If I seem a little bit punchy, it's because I just got off a plane. I'd planned to be here a couple days ago, but American Airlines had other ideas. So apologies for that. But let's remember the circumstances by which David Bohm himself came here were far worse than that. So I can't complain too much. Of course, we seek to honor David Bohm and his seminal papers on quantum trajectories, which were actually published when he was here at University of São Paulo, or USP, in the 1950s. But as also described in the promotional materials for this event, this is also a celebration of the centennial anniversary of the Schrödinger equation. And so we welcome other viewpoints other than David Bohm's. Bohm himself certainly would have welcomed other viewpoints. And to some extent also, this is really a tribute to Brazilian science, which flourished in the decade that Bohm was here. I wouldn't say necessarily because of Bohm, but certainly the people that he worked closely with were some of the proponents and pioneers of this burgeoning of Brazilian science that took place in the 1950s. So all of that was kind of catalyzed and happening at the same time. So for sure, David Bohm left his mark here, even though he wasn't here for all that long, and elsewhere, of course. And we will learn a bit about the fascinating history behind all of that in the days to come. So history is also a part of what this meeting is about, not only of Bohm himself, but also some of the people he greatly influenced. So you'll see in some of the talks some tributes to some of the people who worked closely with him. Now, to be sure, David Bohm's ideas can be approached from a multitude of angles or directions, and indeed Bohm himself did exactly that. Sir Roger Penrose, who interacted closely with Bohm for a time, describes talking with him as a bit like a dispersing wave packet. It starts out very sharp and focused on one specific thing, and then very quickly it just kind of spreads out over all of configuration space. So that was very much the way David Bohm's mind worked. He certainly was not myopic, I guess you could say. So, you know, advantages and disadvantages of that, I suppose. But for sure, you know, Bohm was open to everything. He didn't care who he was talking to, didn't care about their background or their resume. As long as they could have an interesting conversation, you know, then that's what he cared about, and that's what he did. That was more important to him than background or status, say. And it is for this reason that we have cast a very wide net for the participants of this meeting. If you look around and talk to people, you will find yourself interacting with philosophers, mathematicians, chemists, and a frightening array of different types of physicists as well. So we're all here for perhaps different reasons, but nevertheless, we all sort of have some kind of a connection with David Bohm or his ideas. And so I would encourage you all to spend time getting to know each other. I promise you that nobody here knows everybody. And so your goal, your homework is to have an interesting conversation with someone you've never met before while you're here. I'm sure David Bohm would approve of that. Okay, now of course this requires having an open mind, which brings us to another sort of key aspect or attribute of David Bohm. He certainly had an open mind. More than that, even though he felt very strongly that questions are much more important than answers. And so this quote, it's actually not a quote from David Bohm. It's a quote from my co-organizer, Valgir. Valgir, would you wave and let people know who you are? So a lot of you have received emails from him. If you have, you've seen this on his signature field, which I'm sure was there even prior to this conference. But it is a sentiment that David Bohm nevertheless would very much approve of, and which he, in fact, expressed on his own many times throughout his life. So kind of along with that, I would say, and this part might be a little controversial, I would say David Bohm didn't believe in laws per se, at least not in rigid laws that can never change. You know, he was much more interested in things that grow and change rather than things that are static and sterile. And I think that's kind of an important way to view Bohm himself and his approach to life, and also the kind of bewildering, you might say, change of opinion or inconsistency if you look at kind of his thought patterns over time. But you know, if looked at from that perspective, they start to make sense a little bit. I myself never got to meet David Bohm, alas. I did get a chance to meet Basil Hiley before he passed away, who worked closely with Bohm for many, many years. And Basil and I were at a foundational quantum meeting in Vienna in 2013 that some of you were also in attendance for. And I had given a presentation on an alternate version of Bohm's quantum trajectory theory, which is something I developed that has similarities to, but also very profound differences from Bohm's own approach. And, you know, of course, very curious to know what Bohm himself would have thought of these ideas, right? And so I had a conversation, kind of struck up the courage to ask Basil about this. And he was adamant that Bohm would have found it interesting, even though it, you know, was very different from the canonical approach. He was not at all territorial. As I said, he preferred growth and change and kind of the flourishing of ideas in new direction. That's what mattered to him most of all. So of course I was very heartened by Basil's comments. Now, my own interest in Bohmian mechanics, particularly the quantum trajectory theory, did not start until some years after he passed away in 1992 with the publishing of this book, Infinite Potential, The Life and Times of David Bohm, written by David Peat. And the title, almost everyone here knows, is a double entendre that refers to the fact that the quantum potential which he invented can be infinite at times, particularly at nodes. Anyway, this book sparked a kind of a resurgence, or some might even say an initial surge of interest in David Bohm and his ideas. Prior to that, his work had been largely ignored for decades. And the reasons for that, again, are part of the interesting history, which I will leave to the experts to discuss and not really get into myself. One of those experts, incidentally, will give a talk later today. That's Olival Freire, apologies if I got the pronunciation wrong, who also wrote his own biography of David Bohm, which is also a very good read. And if you're interested in kind of the historical side of things, we have a lot of links on the website. Most of the images on the website are actually links. You can follow them. And there's a lot of interesting stuff. Actually, Valgier managed to scrounge up these really fascinating letters. One of them written by David Bohm, the other by Albert Einstein in support of David Bohm and his move to Brazil. And they're kind of heart-wrenching, but really just interesting at the same time. I love the fact that Einstein's letter has some spelling errors, you know, shows that we're all human, even Albert. So again, I will leave kind of the history to the experts, but I just want to make one comment, which is has to do with our current times. And many, at least in my country, have commented on the fact that we're living in strange or even unprecedented times. But you know, David Bohm's story is a reminder that such quote-unquote strange times have certainly happened before in the not so distant past, and indeed are not confined to the past, but can reemerge at any time. So something to keep in mind, albeit a bit of a sobering thought. Okay, one other quick thing, we're going to do a little film strip actually. There's, in recent years, this movie came out in 2020, also called Infinite Potential, about David Bohm. And some of you will know it because a number of the people in this room are actually in the film and or have served as technical consultants for it. In the interest of time, I won't name names, but you can spot them. And I'll show a clip from this film that talks about why David Bohm moved to Brazil. It's just 3.5 minutes long. Before I do that, I also promised the filmmakers that I would plug their latest venture, which is another film called Quantum Convergence, just came out last month. If you're interested, I'm sure you can find it online. So with that, I think we will switch to the clip. Serge, if you could show that.
But while Bohm continued to be preoccupied with such questions, his communist leanings, coupled with concerns at Los Alamos about possible leaks of classified information to the Russians, was to impact dramatically on his life within physics, and ultimately his own view of the scientific orthodoxy.
McCarthyism had suddenly come back to the fore with the Korean War. And McCarthy was trying to get people to testify against colleagues at Berkeley and Los Alamos. And David Bohm was asked to testify, and he refused.
He was asked to give names. He refused to give names. And as a result of that, he was arrested for contempt of Congress.
He wanted to plead the First Amendment, which is freedom of speech. But the lawyers suggested, no, that will be a difficult thing to get out of. You must plead the Fifth Amendment. And the trouble with the Fifth Amendment is that it's essentially preventing you from incriminating yourself. McCarthy was absolutely frustrated with all these people refusing to testify. So he put to the Supreme Court that it should be illegal, to be made illegal or unconstitutional, to plead the Fifth Amendment in this case. And one day when Bohm was in Princeton, a sheriff came and actually arrested him. And he was arrested because he was using the Fifth Amendment. The interesting story here is that he said the sheriff was a very intelligent sheriff, and they had a discussion on the foundations of quantum mechanics as he was driven from Princeton to Washington, which is unbelievable, but typical David Bohm. Then he was bailed, but very shortly after the bail, the High Court ruled that it was not unconstitutional to plead the Fifth, and so he was released. But because he had been enmeshed in this mess, the principal or the head of the university banned him from the campus. Einstein actually wanted him to become his assistant, but Oppenheimer objected. In fact, Oppenheimer saw Bohm in Princeton once and said, I thought I asked you to get out of the country because I think for your own safety you should leave the country.
And I know he did write to Einstein. Einstein tried to help him, but no. The only thing was to leave the United States and go to Brazil. So he had no future in the States. He just had to leave, and that was it.
When he got to Brazil, the American authorities took his passport away so that he could no longer travel.
David Bohm left the US because he was a victim of McCarthyism. He lost his position at Princeton University and was unable to get another job in American universities. He came to Brazil because at that time there were Brazilian physicists at Princeton who invited him to teach at the University of São Paulo in Brazil.
Exile was a chilling experience. At Princeton, he had been surrounded by friends.
All right, thanks, Bill. As you, I'm a little bit dephased at the moment. I got off the airplane at 10 o'clock this morning from overnight flight from Houston. So fortunately, that is the topic of what I will be talking about is dephasing. So it feels very appropriate, I guess. But I did want to talk about the special issue that the Philosophical Magazine is going to offer all of you to contribute to. Philosophical Magazine is the oldest English language continuously published journal, scientific journal, going back to 1795. One of the first editors was Thomas Young, Young's Modulus, Thomas Young, I believe. And so I invite all of you to do this, take advantage of it. It can be anything from foundations of quantum mechanics, more technical things, whatever you wish to contribute, long, short. I'm the editor. I get to choose this, right? But please make it. Please be guaranteed you will be given a proper scientific peer review, possibly by members of this audience, which actually I should say likely by members of this audience to some extent. And just as a caveat, if you've not heard of Philosophical Magazines, maybe you've read some of the papers that have appeared over the 200 years or so, going from many, many papers by Maxwell, papers by Bohr. In fact, I believe Bohr's first publication on the Bohr model, it wasn't called that obviously at the time, but Bohr's model of the hydrogen atom in 1912 was in Philosophical Magazine, and I think one of the first English
papers concerning the de Broglie wavelength hypothesis by de Broglie within Philosophical Magazine. And I'll leave it with that before I fall too far into decoherence land. And
thank you, Eric. We're also very fortunate to have with us today the director of the IEA, or Institute for Advanced Studies, here at USP, or University of São Paulo, who is, and I do apologize for your name, but Roseli Deus de Lopes. Deus Lopes.
Oh, it's just a brief welcome message. I'm going to read because it's better for you if I read instead of doing. So, dear colleagues, esteemed guests and friends, good afternoon. First of all, we want to thank the organizers, Professor Bill Poirer, University of Vermont, Professor Brett Carlson, do Instituto Tecnológico da Aeronáutica, Professor Valdir Guimarães, Instituto de Física, Universidade de São Paulo, the support of University of Vermont, including the dinner, yeah, very good. São Paulo State Research Support Foundation, our FAPESP, and Philosophical Magazine. We also want to thank all invited speakers and the audience. It is both an honor and a pleasure to welcome you to the Advanced Studies Institute of the University of São Paulo for this distinguished meeting. Our Institute of Advanced Studies was founded in 1986, driven by the democratic opening in Brazil and by intellectuals engaged in shaping a new society with the following mission: to research and to discuss comprehensively fundamental issues of science, technology, arts, and other areas of knowledge, stimulating the generation of new ideas and contributing to the analysis of social issues and the development of public policies. So, we are particularly pleased to host this event dedicated to the memory and legacy of David Bohm and to the centennial celebration of the Schrödinger equation, two pillars in the history and development of quantum mechanics. It is a great honor for the University of São Paulo to have had David Bohm as our professor at the Physics Institute in the 50s, where he carried out some of his impactful work. His seminal contributions to the theory of quantum trajectories not only opened new conceptual pathways, but also challenged and enriched the understanding of quantum phenomena in ways that continue to resonate today. This meeting is designed to bring together a community of researchers whose work, while diverse in methodology and focus, is united by a shared commitment to foundation inquiry. In addition to those advancing Bohmian mechanics, we welcome participants for atomic and molecular physics, chemical dynamics, high-resolution spectroscopy, mathematical physics, nuclear physics, the philosophy of science, quantum foundations, and relativistic quantum theory, among others. It's precisely this intellectual breadth that we believe will spark meaningful dialogue and inspire new lines of inquiry. Over the coming days, we will revisit both recent and historical developments and explore the evolving role of such approaches. We will have the opportunity to reflect about how quantum mechanics has redefined not only the structure of physical theory, but also the ways in which we think about nature, knowledge, and scientific progress. We hope we can, during this meeting, identify not only the conceptual and technical challenges that remain, but also new opportunities for collaboration across disciplinary boundaries. We sincerely thank you all for bringing your insight, experience, and curiosity to this collective endeavor. On behalf of the Advanced Studies Institute, I warmly welcome you and look forward to the stimulating discussions and lasting connections that this meeting promises to foster. Welcome. Thank you.
Thank you very much, Roseli. Okay, so it's time to begin the scientific program proper. And our first speaker will be Lev Vaidman. Your talk is set up, Lev.
Okay, so thank you very much for bringing me here. First time in Brazil, and I think it's particularly important for me. I'm really academic grandchild of David Bohm. I'm a student of Aharonov, and I met David Bohm several times. This is from, I believe, from Philadelphia, when there was a small gathering thinking about quantum physics with Shimoni, Putnam, Penrose, Dave Albert, and some others. But what I maybe remember most is that in 1889, 30 years of Aharonov-Bohm effect, there was a conference organized in South Carolina. And so I took David Bohm and his wife for one day to Charleston. So I spent many hours driving and discussing physics and in particular quantum mechanics. So one thing, maybe first-hand evidence, because even then I was a believer of many words, but Bohmian mechanics was number 2. So I asked David Bohm why he likes it, what he finds, because for me and for many others, this was a candidate for a final theory. And he almost screamed at me that there is no such thing. He didn't believe that there is a final theory, that humans are never will understand nature, but we can be closer and closer. So he viewed his Bohmian mechanics as a one step toward understanding nature more, but he considered completely nonsense to believe that we will understand the whole nature. Still, I'm in different opinion. I want to be arrogant and believe that humans can understand everything. And I'm looking for a final theory. And so in my talk, I will try to understand if Bohmian is such or many others, or what kind of interpretations of quantum mechanics, which I don't see any reason to make doubts about quantum mechanics, because everything which we can measure and everything we can calculate about quantum mechanics agrees, sometimes up to 10 decimal numbers. So for me, quantum mechanics is a final word. We just have to agree what kind of interpretation it should have. So I will talk about spin in quantum mechanics and Bohmian trajectories, relativistic trajectories, which some Bohmians look on it differently. I will talk about Bittner's cat. He had a friend. And I will try to, I think some of the things can be understood very simple without too much calculation. You just can see on fingers how things are worked. So let's start with Stern-Gerlach experiment. So this is a historical slide, but this is how I can model it. And so if we send a particle with this spin in eigenstate of then we know what we will get. So there's now all interpretation agree. So there is eigenvalue, eigenstate link. If it's up, it will go up into the upper part. So let's see if it will go back, see how these things. So, something is, yeah. Let me. Okay. So what I wanted to say is that sorry, I'm not, it's my fault, I'm not familiar with the pointer. So if we're in eigenstate, if a spin up, we always get spin up. If it's instead spin down, we will always get spin down. Now, if in a Stern-Gerlach, I have a magnet. So one of the idea, what will happen if I'll take this magnet and reverse it? Then naively, to reverse the magnet, it's to make the up. Yeah, this is what's happened when this was the up one. So if we reverse the magnet, what I would kind of expect that up should be down and down should be up. We have a device. It shows this is up. We take a device and reverse it. So now the up is supposed to be down. In fact, I learned it from Dave Albert in his excellent book. But later, Carlo Gerardi told me that this is really a mistake. That what's happening, yeah, you see, if yes, in Stern-Gerlach experiment, this is the law. We have a gradient of magnetic field. When we reverse our magnet, we reverse two things. We reverse the geometry, where the field became stronger, and also the direction. So essentially, it's -1 square. So the reversing the magnet will do nothing. So what we'll have to do, we have to reverse either geometry or direction of the current in the magnet. So anyway, when we do it properly, still, when we do it properly, we reverse the geometry, but keep the direction the same. Here the direction of the current is the same, but the geometry was switched. But now the up is down. And if we start with a spin up, we always get our device will carry it correctly. It's up. So never mind how we perform the measurement. When we have an eigenstate, the spin up will be up according to any interpretation. Things changed when we have a superposition. If I have superposition, when we have superposition, in principle, quantum mechanics tell us that we can get both up and down. But what is good about Bohmian mechanics for me is that it's deterministic. It cannot be that it will not tell me what will happen. So that Bohmian mechanics tell me exactly what will happen before I perform the experiment. However, it doesn't tell me which result of the spin will happen. In fact, it depends. I can use these two options, this way or reverse way. According to the reversed way, the up is supposed to be down, but not for Bohm. If we have a superposition of up and down, then it really depends on a Bohmian position. What will be the outcome? If the Bohmian position, this is Bohmian particle, is in the bottom part of this of the wave packet, it will go down. Never mind if this is down or up result for spin. And this can be explained, I think, in a simple way, because Bohm introduced his Bohmian mechanics with quantum potential because he thought that maybe incorrectly that this can be generalized and bring us to new physics. But mathematically equivalent is a way that it was presented by de Broglie and also by Bell, when we really saying that equation for the velocity of Bohmian position is just a very simple local current defined by the local density, if this is the equation. So when we have a wave packet going toward a magnet, the Bohmian position has to write together with velocity of the wave packet. And if the wave packet is moving to the right, as is, so the Bohmian position will also move to the right. It continues, and now the wave splits. Part goes up and part goes down. The up spin goes up and the down spin goes down. However, the Bohmian equation has to take kind of the average of all these two things. And the average of the part up and up down will give us this essentially will not have vertical velocity. It will continue to go straight. It will continue to go straight when there is an overlap between wave packet up and wave packet down. Until this moment, it goes straight. At this moment, the wave packet separates from the Bohmian position. The next one, you see, the up wave packet is not related to Bohmian position. So the Bohmian position sees only the down wave packet, and it will continue to go down. So, however, if we reverse our device, and now the down, this one really corresponds to spin up, the Bohmian still tell us it should go down. It's exactly the same situation. It doesn't care. We have two wave packets, one up, one down. This time the up one goes down and the down goes up. But anyway, if the original Bohmian position was in the bottom part, so this one will catch it. It will go to the low detector, which corresponds to the up spin. So what I wanted to say is that when we have a superposition of two eigenstates, up z or down z, Bohmian mechanics is deterministic. It tells us what will happen with the experiment, but it will not tell us if it's spin up or spin down. It depends how we measure it. Depends our measuring device. This is, I think, the good way of contextuality in quantum mechanics. So this simple mechanism can explain also what's going on in EPR. Some people call it paradox. We have this non-local correlations which are found a way to Bell inequalities, Nobel Prize. It's very important. And the Bohm give very nice explanation how it happens. So well, we have these two particles, then the EPR state, up, down, down, up. And one is on the left and one on the right. It's turned out it's not always true, but if we consider spin separately, that Bohmian positions are really not related to spin. The Bohmian position of these two particles can be everywhere where is a wave. It cannot be outside the wave, but within the wave it can be everywhere. It might happen that it's in the bottom on the left side, on the left particle. It's also in the bottom on the right particle. Sounds a little paradoxical because we have this in singlet state, we have up, down, down, up correlation. But it might happen that both of them down. This is the formalism allows it. And it shows that if we measure each one of them, let's say we measure left one, because it's in the bottom, it's again, it will go down. We'll have spin down. If instead we will we'll measure right one, and again, similar, it will say that the right particle has spin down. So how Bohm resolves this contradiction? Because if one is up and another should be down. Let's say we measure the right one. Now, if we measure the left one, things will be different. You see, it goes here, goes here, it goes here. Here, there is this kind of separation. But the point is that in the moment of separation, only the wave packet corresponding, you see, we have this Bohmian particle here, and this equation for behavior of this Bohmian particle depends in which part of the wave sits this one. So from now on, it's really related only, since this one is down, only the upper one is relevant. So from now on, it will be caught by the upper wave, it will go up. Oops. So we have this nice treatment. We understand how it all goes. But what is not nice here, it depends who is first. If we measure first right, the left one will be up. If we first the left right, the left one will be up. So essentially, we have this action at a distance in this experiment. If, for example, in B we do nothing, then A will show down. But if we'll measure the B just before the measurement of the left one will go up. So this is the non-locality of quantum mechanics, and this is maybe the main obstacle for me to accept it as a theory. So now the question, do we have differences in different interpretation? Can we observe the difference? Because this is kind of aesthetical or conceptual, which concept I like more. But the question, can we really go to a laboratory and to distinguish between different interpretations? So for this, I am ready to go to some super technology. Super technology is Wigner. Bittner can make experiment of his friend, and he has a cat, a friend. And this cat is kind of clever cat. Wigner taught him how to perform a Stern-Gerlach experiment. And every time he performed experiment and he see up, the cat stands up. If he perform experiment and see down, he goes down. Now, Wigner can perform measurements on the whole system, including the cat. And according to my scenario, every minute he tests the cat together with his measuring device and everything else in the following basis: plus minus. What is plus minus? Plus, it's a superposition with sign plus of cat seeing up and cat seeing down, and minus, of course, superposition with the minus sign of the same. So this is the scenario. Every minute he performs this kind of experiment. So let's see what will happen given this Wigner with super technology. Let's say we start with a superposition up. So according to many words, everything is unitary. It was up. Wigner should get up, and she will see up, and no change. According to Bohm, the same about wave function. So in the wave function, the Wigner will also see up. According to collapse, if we started with superposition plus, Wigner makes plus, so he also gets the same thing. No change between all these interpretations. Then we wait. There is a 1 minute to wait till next measurement. In many words, nothing will happen. Maybe some unitary evolution, which here it's supposed not to change this. In Bohm, also nothing changed. Now, in collapse theories, the idea is that we cannot have cats in a superposition of being up and down. So it collapses to one of them. Let's say it collapses to cat down. Then Wigner make another measurement. In the left side, we started with plus and plus, so for many words and Bohm, nothing new will happen. For in collapse theory, when we start with cat down, there is a chance to get plus and minus. Wigner measures in basis plus and minus. You can get only plus or minus. So he might get minus. So if you get minus, then later again. On the left side was plus, everything is the same. On the right side, this minus may end up with anything but one for collapse theory, but definite. Let's say it was plus. So the next one of Wigner will be again, might be again plus. So what we see that the Wigner have difference in his results between collapse and not collapse theories. But there is no difference between result between many words and Bohm. Here the story is the same. What about the cat? Maybe the cat is really not a cat, but the person has his own mind. The cat, in fact, cat doesn't see the two ways. He sees either he is down or he is up. But again, everywhere he will see just the same. Now, of course, this measurement of Wigner are very strong, that they can change things for cat. Because if we look for cat, let's look for cat here. The memories of cat, every time they might, it's really the same. He has memories that he doesn't have memories. He was in superposition. Always he will have the memory either he up or down already. So, but in every place it will be the same. Now, if you look on the history, in many words there is one history, and there are all this. In fact, even in many words there is no definite history, because in this case we split the word and reunite the word. Wigner's measurement, not in this case. In this case we had the plus and remained the plus. It's all the same. But again, the many words history, it's also cat should be either plus or minus, and there is no diachronic consistency. So there is no definite story about the history in many words. About Bohm, what I draw here that the Bohm was on the left Bohmian position, and then it starts on the right. It really depends on the kind of Wigner, what kind of measurement he performed. Maybe he can perform measurement which will not allow this, but this measurement, how to measure in basis plus and minus, usually will require bring them together, and then the cat can go from up to down by the measurement. So memories are changed by this drastic measurement, which is not strange when we allow the super technology to make this measurement and superposition of different things. Of course, we change the story. But can we think about some difficulties when we don't have super technology, when we don't have Wigner? And this is the story of surrealistic trajectories. In surrealistic trajectories, which essentially it was slightly before, before surrealistic trajectories, even Bell realized that if we have Mach-Zehnder interferometer without a beam splitter, then strange things happened in Bohmian mechanics. This is the story. If I will repeat it, the Bohmian particle go, and then in the place where is nothing, it change its it change its way here, and it's always, if it's 50-50 beam splitter, it always has changed hands. It was in the upper trajectory, it will go to the down. Why? Because here there is overlap. In the overlap, the velocity is 0, so it doesn't go up and down. So it will be caught by the upper one. So this is what we'll get. So this is surrealistic trajectory, because we have this strange behavior here. But it's not surrealistic, because, okay, this is Bohmian mechanics. It became surrealistic when we'll try to look on it and we'll see different picture. So how can we look on trajectory or position of a particle? There is one way, it's just to have a pointer. When the particle comes near the pointer, it flips. So if it splits, the particle was there. Another way, that when the particle comes near our device, this device is kicked. So you see, it's come near, it get a kick, it get momentum. It's not change its position immediately, it will change its position later. And maybe another way, it's just spin flip. If we come to near the particle, we flip the spin. So let's look here when we have this slow detector. So this is what's going on. And the claim is that the slow detector kind of detects the particle which is not there. Because what will really happen, we'll have a Bohmian trajectory which is up, but our detector will say that the particle was down. It was kicked. How it happened? Because when it was kicked, it starts. You see, first we have the superposition. So we come up to this point when the kicked one corresponds the kicked one corresponds to the one which is being here, and it starts moving. So this is the kicked one. But now there is this the whole mechanism happening here. The next one, why it's come here? It's come here because, again, the Bohmian particle of this particle sees two wave packets because it's inside two wave packets. The one which gets the momentum, it still overlaps with Bohmian position of our measuring device. So the same story will happen here. Now, if we'll have a fast one, this will not happen because it will be, this will be normal. This is the story. Bohmian position, the particle was not kicked, and the detector will not be kicked. The detector will tell us. The detector, the final position of the detector will remain here. So it will say that the particle was not here. So here, everything is correct. Things are incorrect when we have a slow detector. And this is why it's happening, because in this moment, this wave packet that doesn't see this one is here, and the Bohmian position in the other one, so it only sees this one. So we'll have this continuation like this. I can put it in dramatic way if I want to ask the following question. Let's say I have a cat and I have a bullet with this physics of this kind of type, slow physics. Well, when I have a bullet which comes to a cat, but it doesn't immediately destroy his body, it just puts some momentum in some of the part of the body. So the claim is that if my mechanism is slow, I can kill it with empty wave. Usually we believe that things are happening with Bohmian position. But in fact, in this case, the empty wave the empty wave kills the cat. Maybe I can repeat it. We have this cat. We send the empty wave go down. But if it's slow, then after some time, really the cat become killed, and the Bohmian position will sit here. I can do the opposite. I can send a real bullet with the Bohmian position toward the cat. But if the cat, if this bullet works slow, it will not kill the cat. So we have this strange phenomena. Really, the Bohmian position goes through the cat. The bullet was there, but he will not be killed. How it might happen? We can look on this like the model of a cat is slow detector. So when we go here, we go here, we go here. Now we kind of make the interaction. So it starts moving. It starts moving, so we got the momentum. It will, if it will do nothing, it will continue, and this will, when the wave packet go up, it's like dead cat. But here, when it's moved a little, it will change hands. So the important wave function here, it was a moving wave function which affected the behavior. But after the overlap, it will change hands, and from now on, it's not moving. It's not moving the wave function. So it will be maybe a little disturbed, but will not be killed. So this is a surrealistic situation with Bohmian particles. Sometimes it behaves like we use the Bohmian particles are there, but they affect somewhere else, and vice versa. So again, for me, why I like Bohmian mechanics, I believe in many word interpretations, but many word interpretations have many words, and for me it's bad property. I would like to have one word. And so Bohm can be considered as a way to single out one average word. So how I ensure that there is a one word? If I'm Bohmian, I have a postulate, but not all Bohmians accept. And my postulate is that the experience of every sentient being, including myself, is only Bohmian particles. I do not experience the wave. So if I do so, then there is only one word, of course, because there is only one configuration of Bohmian particles corresponding to what we see around. And it fits all these pictures. There are some strange properties. Sometimes empty wave kills and not empty wave doesn't kill, but always there is one word. There is another postulate, which is almost equivalent. Bohmians like this effective collapse. So what we say is that maybe we feel the effective collapsed wave function, the one which is not empty. So I put this postulate that empty wave packets are not correspond to experience, but not empty, they correspond to experience, like in many words or in collapse interpretation. So that here everything will be indistinguishable if we talk about normal sentient beings. But maybe interesting to consider a hypothetical sentient being which has a brain made of spins, only on spins. So this is his thinking in spins. So when, for example, he wants to, we perform this experiment and he wants to see if the particle comes near him. So we have this Mach-Zehnder interferometer. Our observer is here with this special brains, which is ready. When it's down, it's ready. He didn't see anything. And if it remained down, he didn't see anything. So what will happen? There is a coupling, and the Bohmian particle is here. So the effective wave function is really here. So he will see, he will find, the particle was near me. So he will know that the particle is near me. There is some strange phenomena shortly after. I consider him macroscopic. His brain is macroscopic. There's many, many spins. So for a period of time, until the particle will come to this intersection, he really believes that the particle was near him. But what will happen after the intersection, since Bohmian particles do not affect, the spin does not affect Bohmian trajectories, the same phenomena of changing hands will happen here. And now he will forget. So from now on, he will forget that he saw the particle. So when you get a click finally in this detector and you will ask him, was the particle near him? He will tell, no, the particle was not near him. So the history here is different. He saw the particle and then he didn't see the particle. So this is kind of differences. In a sense, in the end, he remembers that he didn't see the particle, even the trajectory was near him, the Bohmian trajectory. So the histories in Bohm and in many words are different, because in many words there is only, if again, the history can be done only backward, but the history is the same. The history is, if in many words we saw the particle here, we think that the observer, this robot with a spin brain, didn't see the particle, because in this world it comes from here. And in Bohm, the history was different. So this is the only difference. My original question is, there are differences between interpretation. Of course, there are differences between collapse and non-collapse. But if we talk about many words and Bohm, this is the only difference. If I have sentient observers which have spin brains, even then, it's not any single time difference. It's only history, and then they don't remember. So let's summarize what I think what's good for Bohm and what's not so good for Bohm, and what is my message regarding this question of observability of different distinguishability of different interpretations. Bohm is deterministic theory. It has direct connection between particles and experience. All what we need, the quantum state, its evolution, and then we get particles in the shape of sentient beings, and we'll get the experience. It explains nicely the EPR-Bell paradox and all these things, although it's not covariant. It has single words, which is a good thing. Now, relative to, if I want to compare it to many words, it's addition ontology. It has action at a distance. And it's not clear about surrealistic trajectories if there's a problem or how big it's a problem. I think it is a problem. Because now if I'm Bohmian and I go to buy a position detector, I have to ask the producer how fast it works. If it works fast, it will be good. Everyone will agree. If it works slow, it will give me a wrong prediction about a Bohmian position. Also, it is not clear. I have to postulate that the other words don't exist. I have to postulate this supervenience, postulate about my presence. So there was no time. I hope I'm more or less in time. I don't know. I think I finished. So if there are questions, I will be glad.
So we definitely have some time for questions. I believe Serge is going to run around with a second mic. So just put your hand up if you have questions.
Hi, Lev. Thanks for this. I'm not particular. This isn't a question really about this. It's really about the many worlds interpretation. And something that's always confused me was whether there was the many worlds, whether it needed more and more energy to create these sort of new worlds all the time, and whether in what you're describing, whether there is some kind of energy exchange when when it goes into this new world or whatever, whether there is some energy carried through to that or not. I've never really understood exactly how the energy part of this works.
Some people are kind of upset about the name of many words, and maybe one reason why they're upset, because really it's a theory about single universe. The many words is one simple, it's one essentially negative statement. When we go to mathematical foundations of quantum mechanics and read Van Neumann book, he says that there are two processes, process number 1 and process number 2. Process number 2 is a unitary evolution according to Schrödinger equation. Process number 1, it's a collapse on measurement. So all what many words says, there is no process number 1. Now we are a little in difficulty to explain our experience, but then this is what's left. From physics point of view, unitary evolution as usual. So in unitary evolution, when we perform Mach-Zehnder interferometer with neutrons, for example, and neutrons split in time, split in two places, we never ask what's happened with energy. Now there are two neutrons, MC square of neutron maybe not so small. Well, what's going with the energy conservation? No one asks this question. And the same if it's go to a bigger system. There is any problem with energy conservation. It's not considered. Energy conservation, it's a question for unitary evolution. And we have the standard unitary evolution of quantum mechanics. And the many words, it's just we have to somehow to find the gap between this picture that in fact many things happened. When we send a particle to two detectors, both detectors somehow excited, but they excited in correlation. And we see only one. We have to find a way. But from the point of view of any kind of physical problems, no problems, because from physics point of view, all what many words interpretation says, all physics you study in university is correct, except one postulate. There is no collapse postulate. And so the collapse postulate, there are some problems with energy sometimes. No collapse, no problem with energy conservation.
More questions? Angel, we'll bring it round to you.
So thank you, Lev, for the talk. And now I understand the point of view that were discussing this morning. Now, the objection that I see against this surrealistic trajectory, something that I discussed in many occasions with Basil, is that typically the empty wave is neglected. Now, the point is that in Bohmian mechanics, you need necessarily the action of something there. I mean, there is something that should exist, because if you prevent this part of the wave to be there, you can call it quantum potential or velocity field or whatever, then the trajectory is not going to make ever this pathway. It's going to go to the down detector. So what Bohmian mechanics exactly is telling you is, well, you have a bunch of positions there, and you are mapping where all this flow is going. Part of this flow is crossing the pin splitter. Part of the flow is going downwards. This is an interpretation that actually Bohm didn't like too much. That is why 2 years after his first paper, he published another paper talking about some stochastic causal interpretation. Because in the end, you cannot determine precisely the position of the particle, not because it doesn't follow the wave function, but because there should be something else that doesn't allow you to have this knowledge. So the point is, unless you assume the reality of the wave function as a field, as a real field, there is not going to be anything just down, which is where all this argumentation of the surrealistic trajectories given by Scully and all these people in the 90s, I think, is failing. There is a paper by Hiley where he shows where the trajectories what these trajectories should do. Actually, with some simulations, I also prove that there cannot be just an empty wave there. There must always be something. So the point in the end is this the wave function a real field, or it is something else?
Okay, first, just to comment about your last. The wave function, at least in many words, is the only ontology, the only real thing. Everything
Yes.
is everything.
I agree with you.
Yeah. But now, what you mentioned about how to deal with surrealistic trajectories, I saw maybe one of the first. The Engler's paper was on a table of Aharonov as a referee, and I saw it. I said, it cannot be true. But of course, Aharonov didn't do anything. I did the referee. I read the paper, and I realized that it is true. It is this true phenomena. Dave Albert thinks that it's very shows strengths of Bohmian mechanics, showing very nicely its non-locality. So, but again, I think if you consider standard Bohmian mechanics with a single Bohmian trajectory, I don't think it's a positive property that a particle goes here, but the effect is somewhere else. If I understand your approach correctly, you consider many Bohmian trajectories. And then, for some of them, it's empty wave, for some of them, it's not empty. So if you look on collection, then the empty waves play an important role. But again, I'm looking on a standard Bohmian story with single trajectory, because in the moment you have many Bohmian trajectories, you have the same difficulty like I have with many words. So people prefer to be a single one. I don't like that there are many copies of me. So I hope I answer your question.
Yeah, sure. Thank you.
All right, well, I think that's all the time we have for questions. I'll just make a quick comment to follow up on Angel's point, which is that, yes, it is possible to combine many worlds in Bohmian mechanics, but you'd probably find that to be the worst of both approaches. But it is possible to do things that way. So, all right, thank you very much, Lev, for a very provocative talk with interesting examples. Our next speaker is Osvaldo Frota. I apologize for getting the names butchered here, but Osvaldo Frota Pessoa Jr. from right here from USP.
Well, Well, it's an honor to be here. I'm a philosopher of science. So the issue I'm raising is an issue in philosophy of science. And I want to understand and examine how experiments influence the interpretations of quantum mechanics. And looking in different cases, I came up with around 6 different situations. This concern is something that in philosophy of science we might have when looking at the 19th century and looking at how the different philosophies of science were affected by the advances of science. So as new fields appeared, the different philosophies of science had to adapt. Some of them were weakened, others survived more or less well. So this is an example of a few of those schools in the philosophy of science which tried to explain science, and as relativity appeared and quantum mechanics and advances, revolutions in biology, they had to adapt in a way or perish, right, or weaken. So this is more or less what I want to do in this context of quantum mechanics. Klaus Hensel has a nice work examining how these schools were affected by relativity, special and general. But when we look at quantum mechanics, what occurs basically is not so much that you have all these traditional schools that have to adapt to the new science. This happened a little bit with the Kantian tradition. So the neo-Kantians tried to save Kantian view. And logical positivism also, it adapted in a more or less strong way to the revolutions in physics. But the issues of interpretations in quantum mechanics appeared mainly in the small issues that the physicists were encountering. For example, after the theory was established in 1926, more or less, questions like, what are the properties of quantum mechanical entity before measurement? So that's a problem that appeared, and different solutions were given to that, different interpretations were given to that special question, or how does the theory extend to macroscopic bodies? So the different interpretations started growing from different answers to these specific questions. So the old traditional schools didn't play such a big role in trying to explain what was going on. Okay, so I want to look at interpretations of quantum mechanics. What's an interpretation? So interpretation is a set of theses or images that is added to the minimal formalism of the theory without affecting the observational predictions of the theory, or sometimes predicting new things, but in domains which cannot be experimentally accessed. So interpretations might be indistinguishable. I mean, a new interpretation might not give any new prediction, or it might, in certain situations, give a new prediction. Then we would call it a different theory. But following the common usage, I will call these also as interpretations. Interpretations, they can be tested, right, experimentally, and when in situations in which they do predict something different. Although they are a different theory, I will still call them a different interpretation. Okay, what I prepared here as a preamble was just like a summary of the interpretations of quantum mechanics. most of you know about all of these interpretations, so I wouldn't have to go through them. But let me just mention the first phase of interpretations were more realist phases, but I'll come to that in a minute. But orthodoxy established itself around the beginning of the 30s. 1935 is the date that Niels Bohr finishes his complementary interpretation after the challenges of EPR. And Pauli and Heisenberg more or less agreed with him, at least officially. Parallel to that, there were many instrumentalistic approaches that physicists adopted, usually close to the Copenhagen view, but not necessarily talking about wave-particle dualism and complementarity and all these concepts of Bohr. One of these parallel approaches was named the Princeton interpretation, which is basically von Neumann's approach, which has as a characteristic to treat the measuring apparatus as a quantum system, and then obtain results that are in agreement with Bohr's views. So the Princeton interpretation takes the formalism more seriously, considers reduction of the quantum state, while the Bohr view does not, the ontology of Bohr's view is not so close to the formalism. It talks about the quantum postulate and then complementarity, and there's not really a role for the wave packet reduction in the original Bohr view, but that's another issue. Okay, the initial realism that I was talking about involved Schrödinger's initial wave realism without collapses, hydrodynamical interpretations, Louis de Broglie's realist dualism, I'll call it like that. Einstein's realism was more or less neutralized by Bohr. So these initial realist views were defeated, right? What remained was the statistical ensemble interpretation in America and Soviet Union especially, which had a more classical realist flavor. And one might point out that the idea of London and Bauer and others that consciousness may cause the collapse of the wave function, that is a realist view. So we have some realist views, but the orthodoxy was basically anti-realist, right? Anti-realism refers to the approach in which you only attribute reality to what you can observe and measure, and you don't try to imagine hypotheses about what's going on behind the scenes, the observable scene. Okay, so then in the 50s, realist approach had a comeback, and David Bohm was the first to have an impact in doing this. David Bohm was important because he showed that quantum mechanics can be interpreted in a in a deterministic way, and there was an overall perception that quantum mechanics had shown that nature is not deterministic or something like that, and he had the important merit of showing that determinism is consistent with quantum mechanics. So that was philosophically important. Then you have the relative states. Let me mention also the debates about the measurement problem, which we'll come back to that. And then Bell's theorem also had a funny impact because Bell's theorem didn't go against any of the interpretations, right? None of the interpretations were affected by Bell's theorem, but still Bell's theorem had a big impact in the philosophy of quantum physics. First of all, because of the experiments that he suggested, right? et cetera, et cetera. Then there's the mechanism of decoherence, which was quite important in the 70s and 80s. And the last mentioned the wave interpretations and the stochastic localization approach, which is a realist approach, which became important. Okay, so we have this oscillation between realist and anti-realist. I'd say there's of course, the anti-realists came back strongly with different approaches, not only complementarity, but consistent histories, quantum cubism, Bruckner, Zeiliger's view, and relationism. Okay, so this is like a map of the interpretations. And the question is, how do these interpretations and other interpretations, how are they affected by experiments? So that's the main issue I'll explore now. Well, I'm not marking time. Do you have any idea? Oh, okay. So, so the first point, let's look at David Bohm's 1952 paper. The first thing we note with interpretations is that a good interpretation is not differentiably falsifiable. I mean, in relation to quantum mechanics or the usual interpretations of quantum mechanics, if you have an interpretation which cannot be falsified in comparison with usual quantum theory, that ends up being good for your interpretation. And that's kind of paradoxical, because in philosophy of science, one learns that if you have a new theory, you want the new theory to be testable, right? You have to make new predictions. If not, it's not considered good science, right? That's Karl Popper and all the others. And David Bohm more or less was conscious of that. So he, in this quote, he, I didn't bring my glasses here, so I can't read properly, but anyway, I'll try. Our interpretation of the quantum theory leads to physical results that are identical with those obtained from the usual interpretation. Evidence indicating the need for adopting our interpretation instead of the usual one could therefore come only from experiments, such as those involving phenomena associated with distance of the order of 10 to the minus 13 centimeters or less, which are not now adequately understood in terms of the existing theory. So we see that although he recognized that his interpretation is identical to quantum theory in terms of predictions, still he wanted to give some condition, some argument to say that his theory could, in principle, be tested in some way. And the idea is that this could be done by modifying Bohmian mechanics, for instance, modifying the velocity, the rule of what the velocity is, or modifying some other of the principles, and maybe these little differences could show up as evidence in subquantum domains, and then, in principle, the modifications of Bohmian mechanics could be tested against quantum mechanics. So we see that he was concerned with some kind of test, but recognized that his theory, without these modifications, is identical to quantum mechanics. So this is an illustration of how this first rule, right, applies, and good interpretations are not falsifiable. And we can call this like the piggyback strategy, right, for an interpretation. Okay, so this is different from usual philosophy of science. But on the other hand, there are interpretations that are testable, right? So we have different examples of this. So the first one to be mentioned is Bohm and Boob's hidden variable, stochastic hidden variable theory, in which they postulated in a more or less abstract way additional Hilbert space. And in the end, what they predicted was the possibility of having a certain time when the measurement is done, a certain time of relaxation before the the equilibrium state was attained. So in principle, one could measure, doing fast measurements, maybe one could measure some discrepancy with usual predictions. So this was done one year later by Papaliolios. So he did some simple polarization measurements, but he put these detectors these polarizers very close one to the other, and tested for Malou's law. So the prediction of the interpretation is that some violation could be found, but none was found. So, of course, when your interpretation is refuted, and this happens in science as well, when your theory is refuted, you can always find some ad hoc assumptions to save your theory, right? That's usual. So in this case, one could have relaxation processes that happen faster, so that could save such interpretation. But basically, the interpretation was dropped. No one worked on it anymore, I think. Another case, I think this is more classical, famous cases from the de Broglie school, the Portuguese physicist José Ramalho Croca and co-workers basically had the idea of trying to find effects of the empty wave when you have entangled particles, assuming that they maintain their coherence. So if you separate one of the particles and you have an empty wave, then you get that empty wave and you try to make some interference effect with the other particle. And their approach, well, the de Broglie school at this point was working with waves only in 3 dimensions, even when you had two entangled particles. So that imposed certain differences in relation to what quantum mechanics would predict. And so Croca and his group thought up of a nice experiment, and a year later, Mandel's group in Rochester ended up doing the experiment. This is the Mandel group experiment. And the result was that the predicted effect did not occur. So quantum mechanics was tested positively, and Croca's interpretation was falsified. Again, Croca argued that he came up with some ad hoc assumptions to try to save his theory, but it was more or less dropped. A last case is someone from Brazil, Vincent Bohmian, an American who worked at Unicamp, analyzing Bell's inequality. He had the idea that maybe when the experiments are done, the particles, they leave a trace in the ether, in the medium, in the vacuum, whatever. And so that when the following pair of particles is emitted, there's some kind of a memory registered in the vacuum that the particle picks up, and that could make this a local realist theory violate the Bell's inequality. So that was a nice idea, and he came up with an experiment to test it, and basically it has to do with relaxation times as well. And Sumhammer did the experiment with neutrons. It's a Mazender experiment, and you have a shutter, and anyway, the end result was that Bohmian's interpretation was falsified. So these are a few of the cases in which interpretations, which in fact are different theories, but anyway, considered interpretations, they have been falsified. If you have any other examples, I'd be happy to learn about them later on. Okay, so this is a second situation that can happen. This is something usual in philosophy of science, of course. Now there's a third comment which has to do a little bit with Vaidman's talk. The issue that, well, some interpretations have the same predictions, but some interpretations give different predictions, but in domains in which you cannot have experimental access. Right? So that's a situation. One example has to do with comparison between, well, concerning the measurement problem. Okay, so London and Bauer, with his subjectivist interpretation, and also Everett's view, would say that when you do a Stern-Gerlach experiment, then there's a detection, then there's an amplification, and a photomultiplier here, then there's a registration in a macroscopic instrument, and finally someone observes. Right? So that's like the chain of measurement between the object and the observer. And we have a superposition of the atoms here. But how far does this superposition contaminate the measuring instrument? And different answers constitute different interpretations. So London and Bauer would say that the macroscopic instrument does enter into a true superposition, while the views that I call objectivist views, which were very popular in the 50s and 60s, maybe Daneri, Langer's, and Prosperi's theory is the most discussed. And they claim that amplification is sufficient to destroy or to cause a collapse, right? There cannot be a superposition of macroscopic objects. Amplification involves putting energy into the system. This energy is completely incoherent. Anyway, and of course, there's the detail that this has also to happen in negative result experiments, right? So even if there's no effective amplification, if one of the detectors is removed, and I don't detect anything in the remaining amplifier, and I infer that the particle collapsed to the other trajectory, still that is considered an amplification because, well, that can be justified in different ways. The wave function interacts with the measuring apparatus, although there's no transfer of photons or quanta, but still there is an interaction that can be considered. I mean, the authors later on had to recognize that this is a possibility. So. Anyway, so we have two different views on when a state collapse occurs. Of course, these are realist views, right? You're assuming that the collapse is something real. It's not an anti-realist discussion. For the anti-realist, this discussion is, you know, is pointless, right? But so we have different interpretations here, but they cannot be tested. Okay, a fourth situation is more, I think, relevant, and it's the issue of experiments that lead to the necessity of refining your interpretation. So, of course, this is common in science as well. Like you have a research program, you have the nucleus of the hardcore of your program, but of course, whenever your predictions go wrong, you can manipulate, you know, the protective belt of your research program, and in that way adapt to new experiments. So this we can find this happening with the complementary interpretation. The idea that a quantum experiment can be characterized either as a particle phenomena or a wave phenomena. Wave phenomena gives interference patterns spatially or temporally, while a corpuscular or particle phenomena allows you to infer past trajectories. So Bohr stipulated that an experiment is either one or the other. never both, and that these two aspects exhaust everything there is to say about an electron. But of course, in 1935, he had to consider that the phenomena involves the whole apparatus, even far removed parts of the apparatus make the totality of the phenomena and all that. So that was already a refinement. But later on, something curious happened, as everyone knows, the appearance of intermediary phenomena. The idea that a phenomena can be partially wave, partially corpuscular. And after some time, that became something quite simple and obvious. An intermediary phenomena is characterized by a visibility between 0 and 1. So this, in the figure here, is depicted by these regions in which the oscillating pattern does not go to 0, right? So that's, the visibility is not 1, and it becomes 0 when there's no more oscillation. So we see that in a typical two-slit experiment, most of the pattern that we see can be considered an intermediary phenomenon. And okay, so that is a big problem for complementarity. I can say, luckily, or for the interpretation, the scientists who discovered this were very interested in attacking the complementary interpretation. And in the end, you can say, well, if you have a phenomena which is 30% particle and 70% wave, there's always a complementary setup which reverses these percentages. So the notion of complementarity can be saved in this sense, right? So that's typically a refinement, an adjustment of the interpretation. One would expect maybe that this could be a fatal blow to the interpretation, but complementarity has had a lot of success in quantum optics, in entangled systems, so it's still strong, right, I'd say. Another refinement, which Bohr didn't think of, is also quite simple. This is an example of the fact that a phenomena, wave or particle, which for Bohr applied to the whole of the apparatus. In fact, you have to consider which detector you're considering. So detector D2 here is clearly associated with a corpuscular phenomenon. There's a filter, a 0 degree filter there, which selects, one would say, the path A, right? So then you have a clear path. Every photon that falls in D1, in D2, sorry, you can associate to a well-defined trajectory by path A. While in D2 and D1, this is a quantum eraser, and at 45 degrees, it erases the path information introduced by the first two polarizers. And if you have in H1 here, if you have a phase shifter and you oscillate it and introduce a phase phi, you can see that the phase remains in the final wave function here, indicating that you can have a temporal interference pattern if you oscillate this phase, if you shift this phase constantly, indicating that the phenomena in D1 is a wave phenomenon. So you have a wave phenomena here and a corpuscular phenomena down here. So that's like a small challenge, but of course, this is easily incorporated into the interpretation, right? And a final challenge was Afshar's experiment, right? And now Afshar came as a challenge. I mean, he was really attacking complementary interpretation. And this shows that the discussion concerning interpretations, as you all know, also involves emotional, intentional aspects, right? So someone can consider his new theory as a new interpretation, and he can sell it as such, or he can just consider, oh, this is just a new way of doing mathematically, of analyzing what's going on. So this also is something that appears in the discussions of interpretation, this emotional, intentional aspect. So Afshar launched a challenge. This is his experiment. It's basically a double slit experiment, right? Here in one we have the two slits. So if over here you put the screen, you would have an interference pattern, and you would say that it's a wave phenomenon. Okay, but now there's one first modification, putting a lens here. So there's a lens here. This lens has the effect of making the detectors here, D1, D2, be able to distinguish which slit is associated with the detected photon, right? That makes sense, right? The drawing makes sense. So we would say it is a particle phenomenon, because measuring in D1 and D2, I know from which slit the photon passed. But then Afshar's idea was to put a grid, G here, a thin wire in every position in which interference, destructive interference is taking place. So this could be done in a nice way so that almost none of the light would be absorbed or deflected. And the fact that you're putting a grid and that the grid does not absorb any of the light shows that there's destructive interference taking place, so that would constitute a wave phenomenon. So you would have a wave and a particle phenomenon at the same time. So that was the challenge, and new scientists contributed a lot to make this well known, and different responses were given. But the response I want, it seems more or less simple and straightforward, is that the complementary interpretation has to adapt to this challenge and recognize that to attribute a wave or particle phenomena, you have to consider the portion of your apparatus. So in this case, in relation to 1 here, my detection is able to distinguish the path, so it is a particle phenomenon in relation to 1. But in relation to 2 now, what I have is a wave phenomenon. In relation to 3, of course, I'm measuring position, so I have the information of position. So in relation to 3, the detector is always a particle phenomenon. So that's the adjustment that complementary interpretation can do to adapt to these new experimental challenges. Okay, so that's an example of this fourth. Now, I think my time is probably running out. You can help me. Okay, right. Okay, so let me just mention these last 2 points. This fifth relation between experiment and interpretation is something curious. Is the fact that sometimes an experiment can create a new interpretation. And how did this take place? Well, with Bell's theorem, let's just jump over this. I'm adopting the standard interpretations for Bell's theorem, which is that you either abandon locality or abandon realism. Not everyone accepts this, but this is what initially was the basic interpretation given. So what happened was that local realist interpretations were prohibited, right? Were ruled out. And in fact, there weren't practically any interpretation that was local and realist. But since the challenge now was given, Marshall, Santos, and Sellery came up with a way of constructing a local realist interpretation. So they created an interpretation just to show that one was possible, that would be able to explain the results of the Bell theorem. And their idea was to work with an enhancement hypothesis. So the usual derivation of the Bell inequality in optics in the 70s made use of polarizers. So there was this hypothesis that if you put a polarizer, it can never enhance the intensity of light. It can only diminish the intensity of light or have no effect, but never increase. How can you You put a barrier, how can you increase what's the flow of a fluid? That can't happen, can it? But they said, well, but our hidden variable theories is such that this does happen. And we have a situation that's similar to that in optics, where I put a filter, polarization filter at 45 degrees, and a situation where no light passes, and I put this barrier and out light passes. So that would be analogous to the enhancement hypothesis. But of course, in their model, there's not these other filters that play a role in this example here. But that's basically their idea of making their interpretation, being able to match the Bell situation. Okay, and the final experiment here I want to consider is, I'm not going to talk about this, but has to do with a curious situation which happens with the Wigner-Friend thought experiments for entangled particles, which was proposed by Bruckner, and experiment was made. So this was very interesting because the interpretation suggested a new experiment, which is interpreted in a certain way. The experiment is done, predictions are confirmed, and so there's like a broadcasting to the community that this new experiment is consistent, say, with a certain interpretation. But the fact is that the other interpretations also can explain equally well what's happening. So this is a curious situation. So like in the media, when you read about it, it seems that the experiment favors an interpretation, but in fact, that's not the case. But I mean, it's not. I mean, the interpretation had the merit of thinking of this experiment, which was a new experiment. So it is an interesting situation. Well, this is experiment Poirer et al. And basically what's behind the hypothesis that's in play here is whether, you've seen it before, is whether a macroscopic measuring device can be considered in a superposition or not, before observation, before some other measurement. So we've seen that the objectivist view that I mentioned before would say that no, a microscopic object or Wigner's friend, being a human being, can never enter into a superposition. Why? Well, because of decoherence, because of, well, there's all these discussions. It's an interpretative issue. I don't have to go into it right now. While the defenders of this relativist view would say that, well, the conclusion, let me see what's their conclusion. So let me just get to. So Bruckner, in his prediction, concludes that there cannot be facts of the world per se, but only relative to an observer. So that's a relativist or relational view, and relational views are very widespread nowadays, which is interesting. These experimentalists conclude they reject the objective interpretation of the measuring apparatus, which typically comes at the cost of introducing new physics that is not described by standard quantum theory. So they're saying that if you claim that a macroscopic instrument cannot enter into superposition, you are introducing new physics, while of course the objectivist would claim the contrary. So anyway, but it's a interpretational debate. I think my time is up, is that correct? Yeah, so I was just going to comment on the Foreman thesis and some other interesting stuff, but so this last point was summarized that some experiments are suggested by an interpretation while not affecting its rivals. So these are the preliminary conclusions are the 6 situations I mentioned. I don't have to repeat them; they're over here. So thanks a lot.
All right, questions for Osvaldo? We'll bring a mic to you in a sec. Behind you.
Hi, so thank you for your talk. Concerning the Bohm's theory, there is this approach of Anthony Valentini, which he says that if you say that the initial conditions for the Bohmian trajectories are not given by the Born rule, then you can have some instances where the Bohm interpretation could give different results from the usual comparing interpretation. So I think this is also something very interesting. But of course, almost everything in the universe is already in a quantum equilibrium state, as they say, but perhaps some other systems coming from cosmology or something else could perhaps shows this depart from the Bohr rule and some typical state. So I think this is something nice to be commented.
Okay. Thanks.
So you were saying that in the double slit experiment, you had an example of like intermediary phenomena, you called it, between wave and particle. Can you explain that again, please?
Well, the reasoning is related to the visibility of the interference fringe. So if in this domain here the visibility is less than 1 and greater than 0, then that would constitute a intermediary phenomenon. And you can think, like, if you detect a photon here, isn't it more probable that it came from this slit? So you have some information of trajectory.
I prefer thinking in terms of electrons, right? Because light is a thing about itself.
Okay.
But if you do the experiment with electrons, you get like point-like impacts, right?
Yeah, yeah,
and
sure.
then
Yeah.
also you get this these interference fringes when you do a lot,
Right.
like when you do the experiment over and over again.
Yes, that's correct. But if you have a pattern like this, then you could, I mean, of course, this is a histogram of the sum of a bunch of electrons, right? A big number of electrons. So if you detect an electron here, and you ask, well, is this, do I know from which slit it came from? And I'm assuming that, you know, each slit has an independent distribution of this form. So since it is closer to this slit, and the probability is greater that it came from this side than from this side. So you can say that, in part, yeah, you have some information of from which slit it came, but still have interference fringes. So it's also partially a wave phenomenon. Anyway, but we can talk about that later on.
Sorry, you run out of time. Could you just flick back to the Stern-Gerlach experiments before this? I don't remember what slide. Ah, there it is. Could I just ask you, just purely a question about the way it's set up is, you've got a Stern-Gerlach magnet, and then, I'm sorry, I can't see it quite clearly, but you've got two detectors set, I presume, to pick up a +1, -1, or half, -half, whatever, particle.
Yeah, it's just like a metallic plate, which has a big number of electrons. So you could ask, well, in this phase here, would you say that collapse happens since the atomic system is interacting with the?
I'm sort of being a bit. We actually do this experiment, and we use a multi-channel plate detector. But anyway, that's by the by. But what I'm trying to figure out is, you're saying that the output from each of those detectors, regardless of what the nature of the detector is, then goes through some amplification stage and so on, which if by looking at that is a photomultiplier tube.
Yeah, that's incorrect, of course. This is just
the suggested diagram. So are you saying that there's somehow, not you, but is this interpretation suggesting that there is some kind of not interference, there's some kind of coherence between the two photomultiplier tubes, or did I not? I didn't quite grasp what.
Yeah, that's this view here. I mean, the London and Bower traditional view.
What I didn't understand what they meant.
Yeah, they want consciousness to be responsible for the wave function collapse.
Okay.
And so they imagine that this is isolated, so quantum mechanics would apply to this whole system, even though it's a macroscopic system.
Okay.
And so they come to the conclusion that the apparatus can be in a real superposition.
Okay.
So that's shared by many worlds. Interpretation sees this as happening as well. But for, I don't know, experimental physicists, or, I mean, this is usually considered kind of exotic, so usually this more objectivist approach.
Well, the thing is that what you would do is obviously have your detection system and so on, and all the other gubbins that goes with it. But ultimately, it sits on your result sits on a computer screen, because the detector gives you individual points.
Right.
And it's really interesting actually when you see it build up, because it builds up over a period of time, and they are literally coming out of random. You think to yourself, where the hell is that going? And it's one's going up there, and of course you get rogue particles which fly off and then end up all over here somewhere, because that's your background noise. That's what happens. And the same with your interference pattern, which we've done also, is that the particles just appear literally randomly, but you just leave them there, and of course over a period of 10 minutes or whatever, gradually you see the picture build up that we would be familiar with. And so I can't quite see how they're saying, well, actually, the collapse happened in my brain, because if I left the room, I'm assuming that this computer will actually, the screen will still light up and will still do stuff. You know what I mean? It won't. It's not affected by me staring at the screen and watching the bits come up. So I find that a bit odd.
No, I agree with you.
Do you see what I mean?
No, I agree completely. But scientists like, Wigner for a time, and Heitler described a situation similar to the one you're describing. Imagine photographic plates, two of them, and one goes to Japan, the other stays in Europe. And then the collapse, according to this subjectivist view, only happens when a human being opens the photograph and actually looks at it. It's completely exotic, but it's a popular view. I mean, people outside physics like this.
Sorry, I've forgotten your name down. It's about electrons. Because I think I'm right in saying the original experiment was done by Duker and I forgot the other guy's name in Germany in the 50s, and they showed actually where they got the coherence. I won't go into all the details, but they actually show the photographic film in strips, and it starts off and there's nothing. It's basically nothing there, and as they get the coherence increase, you see it appear. It's about I think it's 5 or 6 different photographic strips, and about halfway down you start to see the pattern appearing, and then gradually it gets there. I mean, it's an absolutely superb experiment. I would recommend anybody who's interested in this stuff to read it. And I do have the other guy's name in my notes. So, anyway, I recommend it. You speak German? No, I've got the English translation.
All right, well.
The one use of trains and planes is you and Google German, whatever, can sit there do interpretations of papers if they're not in the right language. So good use of a plane journey.
All right, well, I think it's probably time to head off to our coffee break. I have a few quick announcements and some questions and comments for you, but I'll hold off on those in the interest of time. All right, let's sit back down. Still 2 more talks to go. So the next talk will be given by Eric Bittner from the University of Houston. Eric was actually instrumental in getting me involved in Bohmian mechanics quite a number of years ago. There was a SECAM meeting in Lyon, France, that I forget what the nominal theme of the meeting was, It was a computational chemistry meeting, but it was essentially all Bohmian mechanics talks. Oh, and also some Wigner-based stuff to boot. So I was already a huge fan of Wigner, so I was in heaven already. But then when I learned about this new Bohmian mechanics thing, that just tipped me over the edge. That was also my first international talk as an independent faculty member. So something like that makes a big impression. Anyway, Eric, all yours.
Thanks, Bill. Yeah, actually, there's a couple parts of that meeting. It was organized by Bob Wyatt and I, and I think it was this, for lack of better ways, stuff that Bittner and Wyatt were interested in at the time. You know how these meetings go. But anyway, it's probably called quantum dynamics and chemical systems or something like that. But anyway, the banner page here is a little bit of advertisement for the journal. The QR code, we're going to leave this. I hope we can leave this picture up a couple times throughout the meeting. You can scan to submit your article, submit to science, right? And so on. So let me find the clicker. Here we go. So go forward. How do I go forward? Hello. Second one. That one. Oh, yes. Okay. And as I was just mentioning to Bill, a lot of us in this room trace our Bohmian roots, if you wish to call it that, back to this paper by Bob Wyatt, who was professor at University of Texas. I was a postdoc, not with Wyatt, but with Rosky back in the 90s. And Bob and I, in the early 90s, it's amazing to think that that was 30 years ago, would have lunchtime conversations, which eventually led to his seminal paper with Courtney Lefroy on quantum wave packet dynamics with trajectories, which I think a lot of us read back in the day with a lot of enthusiasm. And eventually he wrote a really interesting book on quantum dynamics with trajectories, with the idea of using these little Bohmian trajectories as a basis for doing grid-based quantum mechanics. And that's what I got my teeth cut off, and a lot of us doing, trying to do quantum simulations of wave packets moving around. And I was actually sort of surprised. I did not write the Wikipedia page, by the way, but I was sort of surprised to see that this paper by Bob and I was listed as one of his significant publications, which I'm really quite happy with. Back in 2000, 25 years ago. That's hard to imagine. But anyway, what I really want to talk about today is not so much Bohmian mechanics. I've moved way out of this field, but I do like to think about more ontological, maybe philosophical issues in quantum mechanics, and that is, can noise enhance entanglement and coherence? Generally, the answer should be resoundingly no. We can all go back and drink some beer or something at this point. But it sort of gets to a couple interesting questions. What kind of information is within a quantum ensemble? And some ideas that I've had in terms of detecting fractional statistics using coherent spectroscopy, which is nonlinear spectroscopy in the ultrafast regime. And I probably won't talk about topological effects. But an interesting kind of question that has been driving my research in the last maybe 10 years has been what kind of non-trivial quantum effects can be detected using either classical or quantum light, and using this as a way to inform spectroscopists that I collaborate with. Here's an experiment that maybe you can do to detect this interesting uniquely quantum mechanical effect that is not necessarily trivial to detect using normal spectroscopies. Some of this work was started when I was an ULAM scholar at Los Alamos a couple years ago, and again, if you have like a year of your time to spend and want to spend it in Los Alamos, please do so. There's a great quote in the Oppenheimer movie where they're horseback riding with his girlfriend or something like that. He says, I really wish I could figure out a way to combine my two great loves, science and New Mexico. And Los Alamos National Laboratory was born of that love. Okay. And the desire to build an atomic bomb. Anyway, so quiz time. This is, again, my opinion. Maybe we can survey the room a little bit. What is the longest continuously funded, quote, continuously funded, non-military science research project? Anybody want to take a stab at this one? Okay, it's not quantum computing. Okay. Okay, it's actually timekeeping. and having an accurate precision time stamp. And the first grant, if you want, government grant, competition, open competition goes back to don't hit that one, 1598 by the Spanish and Dutch governments. Why in that year? This is the year roughly, the age of sail. This is when people were exploring the world, and you needed to know how far east or west you were of a particular meridian. And really, east or west of a meridian is a problem of timekeeping. Because you measure the star transiting a meridian, let's say the Greenwich meridian or the Paris meridian or the meridian passing through you right now, and you time that, you keep it in a logbook, and then maybe 15 days later you're at sea, and you keep track of it very accurately. Say, okay, well now I'm measuring this star, and it's here this many times. I'm measuring the time difference between when I measure it here and measure it at someplace else. And so you keep a log of this. You develop what's called the Nautical Almanac, which, I'm a sailor. I used to have a hard copy of the Nautical Almanac. You have to buy it every year. Now you can get it on your iPad. But it would be a tabulation of star transits through the Greenwich meridian. And you can calculate your position at sea using this kind of data and some precision instruments. So why was this important? Well, in 1550, the best clocks that we had were only accurate to 15 seconds per day. Now, let me put this into perspective as again, a sailor. 15-second error, okay, so what? You're a little bit late for lunch. But but think about it this way: an astronomical object moves across the surface of the Earth. Its zenith position moves across the surface of the Earth. The Earth at 900 knots. A knot is 1 nautical mile per hour. A nautical mile is 1856 meters. Okay, so that's 1 degree or 1/60th of a degree. It's 1 minute of latitude. That's a big difference. That's a big distance. So this 15 minutes. 15 seconds of error could be 10 miles, okay? And this error and not being able to keep track of time at sea is an ongoing problem. And well, nowadays, how many people got here by GPS? We all did. We all got on airplanes because or we look at our Apple Watch and it's got a GPS. You can figure out where you are within 3 meters at any given time right now. That's a luxury that did not exist 400 years ago. So in 1707, roughly a third of the British fleet was coming home from the Americas was lost in 1 day due to a navigational error, where they crashed into the rocks, into the Channel Islands. Apparently, some midshipmen had pointed out this error, and rather than say, "Yeah, congratulations," the captain had him flogged. Lesson to all of you graduate students, I guess. But this led to I got my slides out of order a little bit. The Navigation Act, the Longitude Act of roughly, I think it's 1711 or something like this, where Parliament established a competition that said, okay, we need to be able to develop a clock to be able to keep time at sea down to this degree of accuracy. If you can get it down to a second per day or half a second per day, you get the big prize, which at the time, I think in today's dollars would be about $1 million or something like this. And that was, the first stab at this goes back to Huygens. This is Huygens' early clock, where he noticed in an earlier competition that you could synchronize pendula if they were connected by a common beam. And this would happen spontaneously, and a beautiful paper, series of papers submitted to the Royal Society. Again, 1610. This might be the earliest paper I've ever referenced in any of my own scientific work, where, again, concerning the use of pendulum watches for determining longitude at sea. And this is a very complicated classical nonlinear problem that has continued to be analyzed over the years. This competition was eventually won by this guy, John Harris. It took quite a bit of effort and lobbying to convince the Royal Society to actually give him the prize. I eventually took it after the king to say, yeah, this guy won, give him his money. And just to sort of prove my point that this is one of the longest running scientific developments is, here's an article from 2025, this year, where NIST sets a new atomic clock standard of 1 second per 100 million years. This is the most accurate clock ever produced. And just to maybe get a little bit of a historical accuracy, his clock was 0.2 seconds per day at sea. And the way they would do this, he had to make 2 copies of his clock, one that was kept in London and one that went to Jamaica and back. And then they calculated the time differences between the two, and it was amazingly accurate. Now, if you know a little bit about how clocks work, you can compensate for the error, assuming that it's linear in time. Your time man, or your Timex Iron Man that you can buy at the local drugstore will get you to about 1 second per day. That's so not bad. What does this thing look like? Well, here's his earlier clock, and you can see the origins of the Huygens pendula inside of this. This is at the Greenwich Observatory. I had a day, if you ever have a day in London and you have nothing to do, which is hard to imagine, go to the Greenwich Observatory and spend a day there. I spent so much time photographing this particular clock that they started asking questions, and eventually I convinced them that I was trying to like do some science with this, and they let me go back, and I actually got to wind this clock. It was really pretty cool. This was the Harrison chronometer that won. This is the guy that keeps time at sea. He had to build two of those. Now, if you're an experimentalist, I want you to pay attention to the amazing detail of all this. And if you're, laser tables don't look like this today. This is an absolutely, not only is it a precision scientific instrument, it's a piece of art. Some other pictures. So here's the prime meridian. It's a prime meridian because there's this telescope there. And I think this was built by Airy. George Airy, and that's the prime meridian. You can stand in the east and west hemispheres simultaneously. Now, an interesting thing is, if you pull out your GPS and look at it, it will not show 00 east. Okay, and this sort of got me to scratch my head. It's like, well, is this why I always get lost when I'm wandering around in the UK? It's not. The real reason is because your actual GPS meridian is located about 100 meters this way, and I believe that is going to be east, because this is facing north of the quote prime meridian. And the reason that it's different is because your GPS uses a mathematical model of the Earth rather than a spherical Earth for calculating your position, and that's why. Okay? It's not because something weird. This is just another picture that I had. There's me playing around. Okay. Anyway, so let's go back to this question. And generally, the answer, like I said, should be no. Absolutely no. Can noise enhance entanglement? No. And here's a reason why. Standard wisdom. Noise in the environment kills quantum coherence because, and this is a model that goes back to 1952, 1953. Kubo independently, Phil Anderson have a stochastic model, and you say, well, let's imagine that your frequency that you're measuring, spectroscopic frequency that you're trying to make, don't hit that button. Your spectroscopic frequency wiggles and jiggles around about some mean due to fluctuations, maybe dielectric fluctuations, other sort of motions of the environment, and it's the averaging of all of these things. Now to create the response function, you need to exponentiate this thing, so you get like a frequency modulated type signal. You put a bunch of these guys together and start averaging, and boom, you get a free induction decay and Fourier transform, and you get a nice peak. And this is all of linear spectroscopy that you need to know for any physical system that you want to get, you want to use. And specifically, what you're calculating is the first order response to the polarization, which you could calculate here, which is how we calculate that quantity. And what's beautiful about this theory is that it has a couple key parameters. One, the deviation about the mean, which is just how far up and down you go, and then some sort of correlation time of the environment, which are the only two parameters that are necessary here. And you can get either a homogeneous broadened limit or a emotional narrowing limit, which gives a Lorentzian sort of line shape. So you can, and this leads to what's called the line shape function in spectroscopy. Okay, so that's all fine. But there's a bunch of experiments that are in the chemical physics literature that suggest that coherence can be preserved by underlying dynamical motions in the environment. And these are just an iceberg's tip of some of the experiments. These are fairly recent ones looking at how the coherence in an exciton that's been created by photoexcitation of a chromophore and that is found in purple bacteria that lives a kilometer below the surface of the ocean, enhances and preserves the coherence in that state, allowing it to sample through the molecular environment and eventually find the necessary part of the antenna molecule to undergo chemistry. Okay, and this is a model and work that goes back probably 20 years or so, work by Graham Fleming and et cetera. But the idea is that there are specific non-dissipative correlated modes of the system that preserve and protect coherence. And this got me thinking, again, thinking along the lines of the Huygens clock. So a simple model. Since this is largely a mixed group of people, we could show some mathematics. And this is a very simple model. So we simply have a stochastic differential equation, which I have here. So dW, this is an Ito type equation. It's an Ornstein-Uhlenbeck process if I slice up this guy. So imagine that you have an Ornstein-Uhlenbeck process that has two Wiener processes that are driving it. And the sigmas are simply the strength of that kick. And Ito calculus, which was again devised about the same time as Kubo and Anderson, 1947, let's say, is generally written with like this, okay? But now let's put something a little funky in. Let's put a correlation parameter so that the product of these two Wiener processes is not just simply dt, but is dt multiplied by a parameter, which I'm going to call the correlation parameter. Again, this is something you can find in a quantitative finance textbook. Okay, this is, if you don't like quantum states, you don't like quantum mechanics, you want to look at your stock market, you think, well, okay, well, your 401k or my retirement plan goes up, your retirement plan goes down sometimes. On average, maybe liberation days when Donald Trump liberated me of half of my my retirement funds. Okay, everybody's probably went down. That's a correlated event. But anyway, you can have correlated events, and if you plug through the mathematics of this, what you find is, again, you have a nice time constant, but you also have an effective strength, if you would. And if your correlation parameter is negative, which it can be plus between -1 and +1, you effectively see a cooler environment. So you can have correlated noise leading to different kinds of dissipative dynamics. So this got me, again, thinking a little more about this. And maybe there is a methodology where you can have noise-inducing coherence or noise-preserving coherence. And again, you go back into the literature, really beautiful papers by Scully. Quantum heat engines can be increased by noise coherence. This is a paper I wrote almost over a decade ago with Carlos Silva, looking at how quantum coherence induced by fluctuations in the environment drive photocarrier generations and heterojunctions. This was an important mechanism for how bulk heterojunction materials can work. And then a fairly recent review by Paul Bremer on noise-induced coherence in molecular processes, a very nice overview of some of this literature. And then just to sort of advertise our paper, this was the cover of JFIS kind of letters that we had this year or last year. But anyway, so here's the basics for quantum open systems. And this is the kind of figure that you sometimes have to show to the organic chemists because they don't like mathematics. But the idea is that in quantum open systems, we study the density matrix rather than the wave function itself. So the density matrix allows you to separate cleanly coherences, which are the off-diagonal elements, from populations, which are the diagonal elements. And it's a far cleaner description of coherences versus populations, classical versus quantum type effects, than simply looking at the wave function itself. And so it also allows you to build in the open quantum system, the unitary part of the dynamics and the dissipative part of the dynamic. Now, again, going back to early papers by Tony Leggett, this could be the Caldera-Leggett model. It could be all sorts of different kinds of models that you want to throw into. This is a very generalized model. The model I like to work with uses the Lindblad dissipator which has this very beautiful form. Lindblad has the property of preserving the trace of the density matrix and other sort of, it has some drawbacks, it's Markovian, and et cetera, but it's a well understood dissipator that one can use. And so it's nice for doing analytical, not even analytical models, nice for doing test case models. Okay, so here's the idea. Let's build a quantum analog of the Huygens clock that has 2 qubits. We can extend this to any number that we wish, but 2 is easy. That each spin, or if you want, each spin is like a clock, and moves with its block vector and some sort of way. And we're going to allow the noise to be don't do that. How did I do that? Okay, well, it'll work. The noise to be some sort of generalized Uhlenbeck process, but I'm going to have some sort of complicated correlation kernel B that I'll put into here. Again, using Ito calculus, we can derive what the dissipator terms should be, and we can derive a Lindblad term that knows about this correlation part. And that's all I want to talk about for that. Now, we can go through that if you want to see how that works out. So you can write out this again as a local Rabi oscillator and some exchange terms. Eventually, we're going to turn the exchange term off and simply look at the transformed environment like the escape mechanism. So every time your escapement mechanism works in your clock, you get a little bit of a kick. Okay, so you can again work out the dynamics and all of this, and we have this quantum analog of the Huygens clock that shows that noise can induce synchronization, which I'm going to show you now. How can I realize that correlated noise? This is an important question. One way that you can imagine anti-correlated noise, which is basically where if spin 1 gets kicked that way, spin 2 gets kicked that way on average, or as opposed to correlated noise where like spin 1 gets kicked this way and spin 2 gets kicked that way at the same time on average. Again, like this on average part that is the correlator right here. So you can imagine putting maybe some sort of shuttle in between that drives one back and forth, or maybe some impurity that is simultaneously tugging on each of the 2 spins, driving it in this correlated or anti-correlated noise, correlated fashion. Okay. Unfortunately, PDF does not allow me to show movies. Otherwise, I could show you some of what these little movies look like. These are always sort of fun to watch. Essentially, what they do is the red and blue dots are the tips of the block arrows on the block sphere, which you would see is the synchronization of the 2 block vectors in the correlated or anti-correlated case, phase locking or phase anti-locking case, if you want. Okay, so go down. Now, but that makes for nice movies, but you really gotta look deeper to see what's going on. So let's imagine that we come up with a measure that tests how phase locked these things are. So a useful measure, first of all, would be the fidelity, so which is a comparison of how closely does your time evolved state look like your initial state. And what we found is that depending upon, okay, he will fix it. There we go, magic buttons, thank you. What we found is that depending upon the initial state that you present the system, you can wind up in either a synchronized or anti-synchronized, or I should say fully phase preserving or phase killing regimes, depending upon the kind of correlated noise that you have. So in this case, if I have a Bell state where like for example, this would be like one of the superposition of 2 triplets, let's say. In this case, so down, down, plus minus, up, up would be the 2 spins. If I present that with anti-correlated noise, you can see that the purity of the state is preserved for a much longer period. This is orders of magnitude longer in time than if I were to have chosen a system that has anti-correlated noise. Now, you can imagine this in the following way, that if I have correlated noise, so what's going on here? So I have 2 states that are both in like the doubly excited state. So it's like these 2 things are up like this. Now, if I have anti-correlated noise, what happens is that, well, really, one goes up and one comes down, one comes up. They sort of go up and down simultaneously. I'm getting that wrong. They sort of they really don't feel anything about the noise. The noise does not drive. Oh yeah, this is what happens. So if one goes up, the other one goes down. One goes down, the other one goes up. So the doubly excited state doesn't really feel, on average, that fluctuation. How and conversely, if I have the two middle states where I have plus minus minus plus minus minus plus, this particular bell state is very sensitive again to correlated noise. Will kill anti-correlated noise. Will kill it. Correlated noise will preserve it over multiple orders of magnitude. And we thought of like ways that maybe one could harness this as a way to improve quantum communication channels. For example, let's say that one of your senders over here, Alice, and she likes to listen to death metal, which is noise in my mind. My son listens to this stuff, and Bob over here likes to listen to cool jazz. Now there may not be any correlation going on between death metal and cool jazz, except for maybe time signatures. And so you can decide upon a particular encryption key based upon the local environments that you happen to know about. And in doing so, you can create quantum encryption channels that are secure for much longer periods of time than you would without any a priori agreement or knowledge of the local underlying environment. Now you can also use this idea to test what is your local environment by simply sending a test signal or a test state to say, okay, look, if I send this state, it decays faster than that state, therefore our environments must be correlated or anti-correlated. So you can test this a priori. Now, the synchronization that I'm talking about, and I apologize that I haven't confirmed to you that this is a synchronization problem yet, but I can show you that momentarily. This is a parity time reversal symmetry breaking effect. We get the time reversal for free because we have an open quantum system, so time is always moving forward in our system. But parity is an interesting question in this case. And parity means that I swap the identity of the two oscillators and nothing changes. Okay, so if I have a Hamiltonian plus Lindblad equations of motion, this is in this particular case corresponds to what's called a Gaussian preserving dynamical map, and PT symmetry breaking is rigorously conserved if I have just simply this particular Hamiltonian. It should be conserved for just about every Hamiltonian that I can think of. And so you can derive, again, equations of motion, and you can also then derive the Lyapunov equations of motions for the covariances. It's somewhat tedious and laborious boson algebra to work through this. If that is something you enjoy doing, great. But if it's not, I have a Mathematica package that I have that does this for you in about 15 seconds. And most of that is time downloading the little package. So you can do these kind of calculations really fast with Mathematica. And so we wrote a paper recently, came out this in March, noise-induced synchronization in coupled quantum oscillators using this sort of idea. And what we find, again, is that before we were looking at spins, now we're looking at harmonic oscillators or bosons. So spins do this, bosons do this, and again, you get this idea that if I have anti-correlated noise that's driving my system, I get in-phase synchronization. So anti-correlated noise gives you in-phase synchronization. Uncorrelated noise gives you no synchronization at long time, and correlated noise. Now these are also taking the noise parameter all the way to its extremum, to plus and minus 1. Now if you choose anything between less than that or within that bounds, this will decay eventually. Because what this also points to is the fact that if you are driving the system, the most correlated condition that you have, you wind up violating fluctuation dissipation theorem, which seems like a big no-no. But yeah, that's just simply what the mathematics is telling us. But I should also point out we're not including any pure dephasing processes in this. This is all dephasing and due to the relaxation term. So there's no pure dephasing in this. Again, that is something that would diminish this particular effect. The time scale depends, of course, on the pure dephasing time of your physical system. But again, the correlated noise gives you anti-synchronized behavior at long time. This doesn't decay, at least within the numerical accuracy of our computers. And likewise, the anti-correlated case does not decay at all. And the reason for that is actually quite interesting. And that is if you look at the dynamical matrix, this thing that's deriving the expectation values of all of the operators, I call that W. And again, you can derive that fairly straightforwardly and find its eigenvalues. You get immediately what's going on. You have a regime where depending upon this correlation parameters, this thing comes as an I underneath the square root, and generally that's a bad idea because as soon as I push that critical push this psi value to some number greater than 0.5 in this little less than 0.5 in this particular set of parameters, what happens is that I start off with two normal modes of the system, one having positive, one being plus omega, minus your typical eigenvalue splittings. They coalesce to a common frequency. But then if I look at the rates in which they decay, once I get to the critical point, to this exceptional point, one decays has a positive decay, which means it's growing exponentially, and the other one is being damped exponentially. So you get one mode and one mode only that grows exponentially. That's the case that has this preserved symmetry, that's this preserved synchronization, and one mode that dies immediately as soon as I'm in this broken symmetry broken regime. Okay. Now this is sort of interesting because as soon as I turn on this the coupling, which was G, which was the dipole-dipole coupling, exchange type coupling between the two oscillators, you start asking yourself, well, where'd the exceptional point go? So if G is equal to 0, I see a really nice, easy to find exceptional point. But as soon as G is not equal to 0, well, where'd it go? And is this truly an exceptional point? Do I still have broken PT symmetry if I have some sort of coherent coupling between the two guys? And the answer to that is yes. What you do is you can do an analytical continuation of the dynamical matrix. Just simply rotate it around, and sure enough, you find an exceptional seam here where you can smoothly connect one dynamical regime to the other dynamical regime by passing through this exceptional seam. And so this really is a PT symmetry breaking effect that leads to the synchronization. So you can adiabatically switch if you can. Now I don't know how one can make. You can't make a correlation that has complex values. It makes no sense to me whatsoever. Maybe, but in principle, mathematically, it's there. So again, let's just prove to ourselves that this isn't just I guess got lucky and picked the right initial conditions. Maybe that was the case. Well, what you can do is you can pick a particular parameterized model that you wish to be Hamiltonian, and the key variable in our model is this interoscillator coupling term, and tune that, and then just simply average over phase space, and lo and behold, you always find this critical exceptional point right at the same value where I get nothing, no synchronization. This is all just numerical noise, really. Then boom, I'm in the synchronized or anti-synchronized regime, and these other guys sort of look around. It seems like, well, maybe we're trying to find it, and then boom, you're in the anti-synchronized or synchronized regime. And you always find that averaging over phase space does not determine where or what regime you wind up with in this particular model. Now, what's interesting in the limit of no coherent, no dipole coupling, no exchange coupling going on between the two oscillators, you still wind up getting synchronization. Now, is this a quantum effect, or is this just classical kicks? Okay, is this actually quantum shared information or not? Because if it is quantum information, then you have to ask yourself, how? Where's it coming from? This appears to be a universal consequence of coupling to an environment. But like I said, realistic systems are still subject to pure dephasing environmental noise, the zero frequency term, if you want, in vectorial theory, which unfortunately does not lend itself to a Gaussian preserving map in this case. So how much of this is due to quantum correlation? So this is the age of ChatGPT, right? So we asked ChatGPT. This was only 3.5, by the way, and it says, well, something went wrong. Contact customer support. Okay, that doesn't work. Okay, so what we do is you ask yourself a question: how much about A can I learn by making measurements on B? And so to do that, you first of all need to describe what are called positive operator value measurements, which are written in terms of these Krauss operators. But again, I don't want to belabor all of this, and that the probability of making a particular observation, answering this particular question, is given by this expression. Okay, so here's your density matrix of the whole system, and you're making positive operator partial measurements on B using this, and then you trace over A to get the probability of making a given observation. This allows you to define a conditional entropy. You know, that again tells you how much you know how much information can I learn about A by making measurements of B. Okay, so this is all great, and this leads to what's called the discord, and the discord was defined by Zurich again almost 25 years ago, and this is the expression that Zurich has for the discord. You work out something that looks like a mutual information, but then you subtract out the classical correlation and decide that everything else that must be left, everything else that's left in the mutual information must be due to quantum mechanics. And this allows you to define a quantumness of your system. Okay. Now, this is an exact measure and great, but it is, for all intents and purposes, aside from a few fairly simple systems, almost impossible to use. Okay. Okay, so how do we know? So here's what we did. We cheat a little bit. So, well, what's our maximal amount of classical information that we can possibly have in our system? Well, that must be preserved in just simply the population. So let's get rid of all the populations, or all the coherences in my density matrix, and strip them out. Let's call rho tilde just my population only density matrix. And then I'm going to calculate a classical mutual information by taking the entropy, the von Neumann entropy of A, the von Neumann entropy of B, minus the von Neumann entropy of the whole system, and use that to define my classical mutual information, and then define quantumness as being the difference between the total mutual information minus the maximal classical information that this system have. This presents a bound on how much quantum information is shared between A and B. Okay? So we tested this out on random density matrices, and just to verify this really was a bound. The green lines are using the are from the random sampling, and I forget exactly why there's this peak here at 0 above 8. I think he said this is just a numerical artifact. The rest of it's not a numerical artifact. So yes, this is a very rigorous bound on the amount of quantum discord the system can have. Now, what was fascinating in this is that if I apply this discord idea to our either spins, this is the case for the spin system, where I turn off the exchange coupling between the spins. Let's just focus on the middle one here. This is as a function of this really the system bath coupling, the gamma, which is the decay time, the coupling between the system and the environment. Basically, as you increase the coupling to the environment, all of the shared information is entirely quantum mechanical, even though there is no unitary part in your Hamiltonian at this point that's facilitating coherent exchanges of information between the two. They're simply picking up their quantumness, their co-quantumness, if you want, due to contact with a correlated environment. Okay. Now we can, for the double oscillator, we can do things a little bit easier. We can see how this comes about because we can calculate the Renyi 2 entropy directly rather than having to do any of this factorization or anything. Renyi 2 entropy is essentially just the log of the determinant of the covariance matrix minus log 2, which is, again, if you have a Gaussian preserving map, this is something that comes naturally out of our calculations. And so you can easily calculate what the mutual information at steady state should be. Don't do that. No, you don't do that. And you wind up getting this really nice expression again, where all of your mutual information. These are simply the covariances of the isolated system minus the difference between the cross terms. And again, you can show that all of the mutual information is quantum in origin once you're in the synchronized state, which I think is a very interesting observation. Now, possible realizations of this. Now, I've been working on quantum light, quantum type matter type interactions, light matter interactions for a very, very long time. And about 5 or 6 years ago, Andrei Pierczynski and I published a paper looking at the idea of generating coherent light in a plasmonic model where you pump a plasmonic array that consists of metal nanoparticles with dressed by quantum emitters. And you can lay out a Hamiltonian that basically, once you've manipulated it around a few times, leads to this picture here at the bottom where you have a quantum emitter coupled to and a series of metal nanoparticles, each coupled to a common reservoir, which is just simply the substrates in which they're lying upon. And eta in our model was our coupling parameter, which was you can map onto this correlation parameter. And sure enough, what we found was that if your dissipative coupling correlation term was basically 0, you wind up with a normal system that just undergoes normal decay. A superradiant undergoes Dicke superradiance, nothing surprising. But once you start pushing this dissipative coupling, and as a function of this Dicke coupling, which is a measure of the light matter interaction, you wind up getting regimes that are what we called at the time lasing without inversion. And I would call these really these autosynchronized broken symmetry states of this particular system. This is an idea that's being pursued by the groups in SINT at Los Alamos to try to make these lasing without inversion type lasers. Yes, I do. I'm just about ready to wrap it up. This is really the last thing I want to talk about. I won't talk about anyons. We can generalize this by saying, well, look, this covariance matrix really imposes an underlying topology of how the quantum states are linked together by the environment. So maybe I can play around with that and devise other sort of topologies, other sort of irreducible representations that lead to protected type quantum computing states that I can then use, quantum resource states that I can use for doing very long time, very stable, error-free quantum computing. And that's a pie in the sky idea. Whether or not that is realizable or not is another question. But given enough money, you can do a lot of stuff. I'm going to end here. We've talked about, we've also worked through fractional statistics. But basically, this is the take-home message. This is correlated noise provides a symmetry breaking mechanism, forcing the system into a dissipation-free regime. I believe this is a universal effect, as suggested by our analytical results based upon spin chains and other sort of things. We've also looked at many, many, many things that I'm not going to talk about here. And there's this really nice possible extension to fractional statistics and topological materials, and it's leading us to develop ideas for how to probe these fractional statistical states using correlated, or rather I should say, coherent nonlinear spectroscopic techniques. And let me just thank the people who did the work. Bave is my graduate student. Here and I are having some discussions over his work. Carlos Silva, longtime collaborator. Hao Li, longtime postdoc. Andrei Pierczynski and I have been working together for probably about 25 years at this point, as with Carlos. And I want to thank not Stanislav Ulam, but basically the fellowship that's in his name at Los Alamos, and then my funding from the Welch Foundation, which actually does still fund chemistry in Texas, and the National Science Foundation for these grants, and my graduate student who did some of the other calculations with this. So thank you. Okay.
So I think we maybe have time for one question, maybe two if they're quick. We're bringing it around.
You mentioned using a spin system as a basis of a clock. And you mentioned that you need to use a kind of analogous escape mechanism to count the revolutions.
Oh yeah. So so what the escapement mechanism does in a physical clock, it's so as your gear turns, you do this little pendulum. It gives a little bit of a kick, and in the Huygens clock, there was that little bit of a kick that led to the synchronized state. So we put this into our model as a way to sort of like constantly being re-exciting our spin system. So every time you get spin down, you get kicked back up. You get spin down, you get kicked back up. Spin down, you get kicked back up. So yeah.
But then it has to couple to the spin system in a controlled way so that it maintains its.
No. Yeah, so in the sort of really old clocks, you have this like pendulum arm that's moving, and that's actually what's advancing the gear that moves as it moves around. I didn't know that until I started digging into clocks, by the way. Yeah.
Just a quick question, Eric. You're using Markovian noise.
Yep.
Yes. Which spectrum?
Pardon?
Which spectrum do you have for the noise, or do you choose for the noise? Because is it white noise or?
Yeah. So at the end of the day, it's a Wiener process for when you dig through Lindblad theory, right? So it's that spectrum. So right. Yeah.
But if you have two white noises.
Right. Yeah. So in this Ornstein-Uhlenbeck case, you have to go all the way back to the beginning.
Yeah, the beginning.
Blah 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 blah. So it's Lorentzian noise at the very end of the days, which you get here, because these are just Wiener processes. So you take the Fourier transform of this guy to get your spectral density, right?
So if it is just simple Brownian,
Brownian motion. Yeah.
If it is simple Brownian noise, why can't you use just in the first equation sigma 1 plus sigma 2, and then just the sum of the two?
Well, because you still have to deal with these Wiener processes, because you have to be careful when you calculate when you're doing Ito calculus with these stochastic intervals. You wind up getting products of Wiener processes, and so it's this trick that comes into being important.
Okay.
Yeah.
No, I ask because in some of the calculations I do when I solve this quantum state diffusion equation, so I typically choose one noise source.
Well, at the end of the day, that's what you wind up getting, right? Because you can say that I have two uncorrelated sources, but one with this and with that. Yeah.
And the other one in the graph of the purity, can you go there, please? No, the previous, this one. Yeah. How long does it keep constant? Or the purity?
Yeah, what is it come back to?
Once you reach the maximum?
What's going on is eventually, so this is purity. So eventually you wind up going back into a pure state because you have one.
Okay, I see.
Yeah. You pick one. Yeah, that's why.
Yeah. Thank you.
Yeah.
Okay, well, I think that's all the time we have. I'll just make one comment, which is that this work has come a really long way. I mean, I've seen you talk on this for a while, and this is really quite impressive. I'm really curious about the universality aspect. We can talk more about that later on. So, okay, well, let's move on to our final speaker for the afternoon. It's my great pleasure to introduce our first plenary speaker of the meeting, Olival Freire Jr. Again, apologize for butchering the name. Again, not in the spirit of what you should do at a Bohm meeting. I'm not going to sort of sing all his praises and accolades. And also, we want to hear what he has to say. But I'll just say one thing. He's currently the scientific director for CNPq. For those of you who don't know, that's one of the big national funding sources for science funding in Brazil. It's also the funding source that David Bohm used to fund his early research in quantum trajectories and such when he came to Brazil. And I believe CNPq was very new at the time. Is that correct, Olival? So not only was it the first funding source for Bohmian mechanics, but it was also, Bohmian mechanics was one of the first projects that CNPq funded. So I think that's kind of neat. Anyway, that's all I'll say. I'll turn things over to you, Olival.
Thank you very much. I want to thank you to you, Bill, Brett, and Professor Valdi for the invitation. And also I want to congratulate you for organizing such a conference here in São Paulo, where Bohm worked at least for mid-51 to the early 55. So almost 4 years here. So for my talk, I want to ask you for making a small change, because I want to speak a little bit about what I call Bohm's scientific style in his quest for understanding the quantum world before talking about the topic of my conference. The topic of my conference is concentrated on the context of Bohm's 1952 interpretation of quantum mechanics. I want to introduce this because I am really concerned that in these days there is a wide recognition of Bohm's intellectual works in broader fields, philosophy, psychology, and others. But I think that this broader recognition many times this lives in the background, in a second plan, the scope and the strength of Bohm's scientific achievements. Then I want to say a few words about this. And these few words, I was motivated by one criticism that was done here in São Paulo by Isidore Rabi in 1952. There was a conference here in São Paulo and Rio de Janeiro. A number of American physicists were here, and Isidore Rabi emphasized that what kind of new predictions you are able to do with this interpretation. Then I think that this idea that Bohm was disconnected with the experimental side of physics is, I would say, a part of the Bohm history that I want to discuss in order to emphasize that far from this, Bohm was very connected with this side of physics. It's true that he had, I would say, daring conjectures in physics, also in philosophy, no doubt about this. But I would say that most of the time, his work was connected with what was happening in the empirical domain. Then I want to show just a few examples. I'm not going to talk about his work on plasma that was very connected with the empirical domain, even his work during the World War II. I think that Iberê Caldas will speak about his early work on plasma here. I want to focus on his work on quantum, on foundations and interpretation of quantum mechanics. The very topic that some physicists think that Bohm was disconnected with the empirical domain. Then I want to cite a few examples. If you take his 1951 textbook, before the paper on the reinterpretation of quantum mechanics, it's in this textbook that we find for the first time the singlet state for bivalent variables. This development, this relatively simple mathematical development was very crucial in all developments, further developments related to the EPR experiments. This was used by Bell in his theorem, and it's the base of all experiments concerning Bell's theorem. I don't want to say that Bohm was anticipating the kind of experiments you could do with the EPR experiment, but I want to emphasize that he was attentive to the
idea of how to take Gedanken experiments and make it simpler. And if it is simpler, it's easier to eventually make an experiment with this. So the paper I want to come back a little later. I like it very much when I think it was Osvaldo Pessoa emphasized that it's true that when Bohm was criticized that this paper did not lead to new predictions, in this debate many times people did not consider that the main achievement of this paper was exactly reproducing the all results that we knew from the non-relativistic quantum physics. This was the main achievement. What I want to say is that Bohm was not satisfied by proposing a new interpretation. He developed a model. Many would say that it's indeed a new theory, but he was satisfied proposing a model and tried to show that this model led to all results that we know from non-relativistic quantum mechanics. Then later, with Aharonov, who was one of his students in Israel. Here we have in 1957 the first discussion of the a possibility of an experimental proof of the EPR experiment. They used the results from an experiment that Wu had performed in the end in 1949, and they arrived at the solution that EPR were wrong and quantum mechanics predictions were right. Nowadays, we know that this paper has a limitation because Bohm and Aharonov did not see the role played by the angles between the that we need to consider to make a distinction between quantum mechanics predictions and hidden variables predictions. Only with Bell that we realized this. But anyway, this is very important. The second work, now it's in the inverse order, it's Aharonov-Bohm. In 1959, they produced what was the most cited paper by David Bohm. Aharonov-Bohm effect was a paper that triggered a number of experimental tests in the 70s, in the 60s, in the 70s, in the 80s. And I can tell you that nowadays, this is the motivation for a number of nominations to the Nobel Prize, not for Bohm, because he's dead, but for Aharonov. Later, Osvaldo Pessoa já he has already spoken about this paper with Jeffrey Bobby. This was no longer the 1952 hidden variables interpretation. It was a different interpretation. But what I want to emphasize is that they got a number, the relaxation time, and this number was checked by Papaliolius, and Papaliolius did not find this number corroborated in the experiments. And a few years later, we had this paper in 1974 by Bohm and Heide, that this was the first paper, as far as I know, to explicitly state that non-locality was the most important effect from quantum theory. And Bohm arrived to this paper, and I want to emphasize the date, 1974. So this was after Clauser and Friedman experiments and Holt experiments, but it was before Frey experiment. Frey experiment, it was 1976. But at that time, he and Basil Heide, they were following the experiments that was being developed, I forgot the name, Wilson, in London. Wilson experiment, the results were published later, but they were informed on these results. And they were able to take these few results and arrive to this, I would say, bold conclusion. And, sorry, back. And finally, as you know, Bohm abandoned the interpretation of quantum mechanics in terms of hidden variables in the end of the 50s. He was discouraged by the reception of this proposal among the physicists, and during the 60s and the 70s, he just abandoned this interpretation. Many of you know that Basil Hiley has recalled that he and Bohm never discussed the 1952 papers till the time that the two students, Chris Philippides and Chris Dildin, come to Basil Hiley to say what is wrong with this paper. And Basil Hiley didn't know what was wrong. He just thought that there was a mistake, but he didn't know what was the mistake. And then Basil Hiley went to study the paper and arrived at the conclusion that there was no mistake in the paper. After this meeting, this discussion, Philippides and Dildin made this kind of what I would say in the biological lexicon, this kind of experiments in silica, not in vitro, because these trajectories are obtained through computer simulations. What is important here is that it was this result from a simulation that led Bohm to resume his 1952 interpretation, and he and Basil Hiley spent all the decade during the 80s dedicated to resume his early interpretation. With some changes, he abandoned the idea of strong role for causality, strong role for determinism. But I want to say that this change was motivated by a kind, I would say, of an experimental result. The works they did during the 80s are very condensed in the last book by Bohm and Hiley, which was published just after Bohm's death. So it's my impression, it's my argument here, is that Bohm not only was a great physicist, but a great physicist with a very important scientific style. Bold conjectures, but very attentive about what experiments were telling him. Just by comparison, if you take, for instance, Jean-Pierre Vigier, who supported with Bohm the hidden variables in the 50s, I would say that a person like Vigier was not so connected with the experimental results as Bohm was. So, this is the first part of my talk. Now I move to this one, the vicissitudes of Bohm's 1952 interpretation. I don't need to summarize the results he did. You are familiar with this, but I want to say that the most important result was that from that time on, physics had a consistent alternative interpretation to the principle of complementarity by Niels Bohr. Nowadays, many times we speak about alternative interpretation, and we include Einstein's interpretation as the statistical interpretation and things like that. But if you see from the historical records, it's difficult to identify a very precise interpretation suggested by Einstein. And you know, Louis de Broglie had abandoned his interpretation in 1928. So no doubt that this was the first alternative interpretation. That's the reason that John Bell in 1981 said a very precise phrase. In 1952, I saw the impossible dawn. What Bell was saying? Two things. First, this paper was a challenge to von Neumann's proof against the existence, the possibility of hidden variables compatible with quantum mechanics. And the second, John Bell was impressed by Bohm's 1952 papers and not by other interpretations that appeared at the time. Now, this interpretation, I would say that Bohm suffered a number of vicissitudes during this interpretation. The first one that we saw this very nice part of the movie where the problem of McCarthyism in Bohm's life was presented. But I want to say that this was not the only context to influence the fate of the causal interpretation. I would say that in the end of the 50s, Bohm's life and ideas suffered significant changes in the transition from the 50s to the 60s. In the wake of the Soviet invasion of Hungary and the denunciation of Stalin's crimes, Bohm broke up his ideological ties with communism. And here, just a short historical comment. Bohm himself contributed to the idea that his links with the communism were very short, just a few months when he was in Berkeley. Sometimes Bohm wrote this. I can understand it because he was a victim of Marxism, of McCarthyism. He did want to emphasize this connection. But, and I also remember that the first time I wrote that this connection lasted for almost 15 years, I had a letter from Basil Hiley, and he asked me how it is possible. Bohm never talked with me about this. But the fact is that when you read Bohm's letters in Brazil, in Israel, to his American friends, it's clear-cut that Bohm was a committed Marxist when he was in Brazil, when he was in Israel. And I make now a kind of announcement. Some of you are aware that Hanoch Freund from the Technion in Israel, they discovered the notes of a course by David Bohm in 1957 in Israel to a kind of a league of youth, communist youth, where Bohm spoke about Hegel and dialectical materialism. So this was 1957. I want to emphasize this just to say that Bohm was a case of, among a number of intellectuals in the 20th century who broke down his links with Marxism in the end of the 50s. In this context, the Soviet army invading Hungary and the 20th Congress of the Communist Party denouncing Stalin's crimes. This was a rupture very harsh for Bohm. When you see his letters, the letter when he wrote to Melba Phillips, speaking about this rupture, Bohm, his letters never were very concise, but the usual letter was 2, 3, 4 pages. This letter is almost 15 pages discussing in a very typical Bohm mood. So if it is not communism, what is the solution for the humankind? It's the usual letter. So what I want to emphasize here is that Bohm suffered not only from McCarthyism, but he also suffered from this breakdown with his previous links with Marxism. At the same time, he had another important aspect in his life that I want to emphasize. because it's true that he was in the movie said that the American consul in São Paulo took his passport, but this had a consequence. Bohm, in order to get a document to travel abroad, Bohm did not want to get the American passport, because the American passport would be done for him if he wanted to come back to the US. As you may remember, 1954, he was here. It was the year that the Rosenberg couple was sent to the electric chair, and it was the year in Brazil when the president committed suicide. It was a year of a very intense political tension. So Bohm needed to travel abroad, and he needed a document. He tried a document from Israel, he did not get, and him and his Brazilian friends tried and obtained in a very short time the Brazilian citizenship. And he got the Brazilian passport, traveled abroad. He only understood that his American citizenship had been withdrawn because he had obtained Brazilian citizenship in 1960 when he was in London. And this was a new problem for him because he, in order to travel to the US, for instance, this nice picture Vaidman showed it, every time he went to the US, he needed to apply for a visa. He only regained the American citizenship in 1986 after a legal process. At that time, Bohm realized that he had no money to come back to the US and never come back to the US. So this is what I'm calling the circumstance, the vicissitudes of Bohm's work. But the other important vicissitude was that Bohm was very pressed by the poor reception of his proposal. And this is the last part of my talk. This number is outdated. Nowadays, it's almost 4,000 citations, which means that by any rate, this is a very good paper in physics. But when you see this number through the years, you will see that in the 50s, almost no citations. And when you read the papers citing Bohm in the 50s, almost all the papers, except a few ones, were criticizing Bohm. Then I think that this poor early reception requires an explanation what Bohm happened with the reception of Bohm's ideas. And then we have here a question that I consider very important. I know that many, even many of you, consider very important what Oppenheimer would have said about Bohm. This phrase, if we cannot reject Bohm, we should forget, something like that. As a professional historian, I am a historian of science, every time I have a document, I prefer the document to the oral testimonies, because we, as historians, we use oral histories, but we use it with a grain of salt. We always want to check the oral testimony with the written documents. And the problem is that we have enough written documents to explain why Bohm was very badly treated by his fellow physicists in the 50s. And then I think that to understand this, the most important case are these two guys, Leon Rosenfeld, who was the Niels Bohr philosophical assistant, and Pauli. They were not the only ones. I talked here about Isidore Rabi, Heisenberg later wrote something, Max Born, but these two are very important because they were very harsh in his criticism towards Bohm ideas. I began by Rosenfeld. As you know, Rosenfeld and Bohm at the time, they were both Marxists, but they did not agree about the interpretation of quantum mechanics. Then Rosenfeld tried to criticize Bohm On the philosophical grounds, with this argument, determinism has not escaped this fate, becoming an obstacle to progress. The physicist who still clings to it, who shuts his eye to the evidence of complementarity exchange, whether he likes it or not, the rational attitude of the scientist for that of the metaphysician. Among philosophers, to say that somebody is a metaphysician is not a very problem nowadays. But among Marxists, this is a very heavy criticism. Now, which is very important, and the documents, these are well documented in my biography of Bohm. Similar to Paul, and I will speak to Paul, but more strongly and with more emphasis, Rosenfeld wrote to a number of colleagues, at least 15 colleagues in the Europe, Soviet Union, and the United States received letters from Rosenfeld criticizing Bohm's ideas. Rosenfeld arrived to the point that he wrote to the Nature's editors suggesting that Nature did not publish a paper by David Bohm. The title of the paper, which was never published in Nature, it's the causal and continuous interpretation of the quantum theory. Furthermore, Rosenfeld came to Brazil, to the CBPF in Rio de Janeiro, and from Rio de Janeiro came to São Paulo and gave a talk, not here, because at the time the Physics Institute it was in another place, gave a talk about complementarity. Bohm was in the audience, and they just quarreled during the seminar. After that, Bohm wrote that he won the discussion with Rosenfeld. Then, this was Rosenfeld. Then Pauli. As you know, Pauli received a draft of Bohm's 1952 paper. And it was Pauli who warned Bohm that these ideas had been developed early, the pilot wave idea had been developed by Louis de Broglie. And Pauli also made a number of criticism, and Bohm accepted this criticism and developed further his paper. Then, you know, with paper part 1 and part 2, I would say that the part 2 was mainly due to the reaction to Pauli criticism. The main reaction is that Bohm introducing the hidden variables not only in the physical system under study, but also in the measurement device. And it is through this approach that Bohm was able to recover all the results that we know from relativistic, non-relativistic mechanics. But when the paper was published, Pauli wrote to Bohm that he recognized that there was no mistake in the paper, and wrote this kind of things. I quote, any effects on observable phenomena, neither directly nor indirectly, the artificial asymmetry introduced in the treatment of the two variables of a canonically conjugated pair characterize this form of theory as artificial metaphysics. And in the case of Pauli, this was the public criticism, a kind of artificial metaphysics, because in Bohm's approach there is an asymmetry between position and the momentum that it's not present in the original quantum mechanics. Then there is no empirical evidence about this kind of asymmetry. But if this was Pauli's dictum in the published papers, Pauli also wrote letters very acerbic against Bohm. So to say that Pauli was very harsh in his criticism, it's no novelty. Who knows Pauli's correspondence knows that he was very harsh for anybody. So what he said about Bohm, I like this one. To Marx Fierce, he commented that Catholics and communists depended on determinism to buttress their eschatological faith. the former in the heaven to come, the later in paradise on earth. References directed to Louis de Broglie, who was Catholic, and at Bohm and Vigier, who were communists. And he also warned, see the detail, Giuseppe Occhialini, who worked when the physics department in São Paulo was created in the 30s. Occhialini left São Paulo after the war. Occhialini worked with light and power in the detection of the P meson. But Occhialini came to São Paulo from time to time. And Pauli had no doubt, who wrote a postcard to Occhialini, warning him that about Bohm in São Paulo and his causal quantum theory. So this was the kind of poor reception. Then I want to discuss now what was the background of the point of view of Pauli and Rosenfeld. Was an attachment to the complementarity views? This is not very convincing. Because Pauli was not so attached to the complementarity principle as Rosenfeld. And secondly, because when you see physics, quantum physics textbooks, there is a study did by Helia Krag, the Danish historian of science, that he shows that complementarity disappeared from the quantum physics textbooks. So what was the problem? I think that the problem, and I am approaching the end of my talk, I think that the real problem was better realized not by Pauli, Rosenfeld, neither by Bohm. The problem was better realized by John Bell. And here is a testimony, but it is not an oral testimony. It's something that Bell left written. Because, so I'm in the 60s, that's why I spoke about the echoes of the poor initial reception. And in December 1966, Bell received this letter from Leon Rosenfeld. 1966, Bell was already a very important physicist at CERN. Bell had already published Bell's theorem and the paper in the Review of Modern Physics. And he received this letter from Rosenfeld. I quote, I need not tell you that I regard your hunting hidden parameters as a waste of your talent. You can imagine that there is no worse criticism to a physicist to say that you are wasting your time, your talent. And I don't know either whether you should be glad or sorry for that. So Pauli was very sensitive to this. In the same year, he and Michael Neuenberg, who wrote a short piece in a fast shift for Victor Vaskop, and they wrote this, I quote, we emphasize not only that our view that quantum mechanics is at the best incomplete is that of a minority, but also that current interest in such questions is small. The typical physicist feels that they have long been answered, and that he will fully understand just how, if ever, he can spare 20 minutes to think about it. I think that this last sentence, in my view, is the best description of what was the problem, the obstacle Bohm's ideas faced. The obstacle was that the physics community did not think that it was good physics to be done with hidden variables. I know that this is an irony because Bell's theory came from our work on hidden variables. And we know that nowadays this work on Bell led to the 2022 Nobel Prize. But anyway, I think that this description for me, it's the best description. It was not a battle between supporters of complementarity versus supporters of causal interpretation. It was a battle between Bohm and later physicists like Everett and the others, who wanted to work on the foundations of quantum physics, and a huge number of physicists who considered that this was a philosophy work in the best, or just did not was good physics. Approaching the end, I would say that this kind of bias in the physics community had a toll among physicists. I and Osvaldo Pessoa, we wrote a paper about one physicist here from the physics department who faced this kind of problem, Klaus Tausk. But I want to talk about Klaus Tausk. I would say that the most telling example of a physicist who suffered this bias was nothing less than John Clauser. And why this? Because I don't know if there is another case of a Nobel Prize in Physics that never got a permanent job in the American universities. And he did not get this job because he was doing experiments on hidden variables. That's the question. He was, by any rate, a good physicist. He was a student of Patrick Deus in Columbia, and then he went to Berkeley. He published the first experimental result and the other results. And we have a number of evidences that when Clauser tried to get a job, the kind of physics he was doing came to the foreground. I just want to cite one of these evidence I have. And I would say that these days, I just read a doctoral dissertation by a French guy, Gauthier de Pambou. He was working on another archive in the United States, and he just discovered 2 or 3 letters in the same sense, in the same direction. But I cited this one, that is the old that I know. So, what was the problem? Bernard Espagnat, who was somebody who supported the work on the hidden variables, he received a letter from the head of physics department at San Jose University, asking, and the Americans who are here and the physicists who know how works the American physics department, selection for the department, the most important, or at least the first step, is the recommendation letter. It's not the case in Brazil. You have this kind of public contest. In the United States, you have the recommendation letter. Then what the head of the San Jose department was asking to Bernard Espagnat about the kind of physics John Clauser was doing. And asked if what Clauser was doing was, I quote, real physics, which means that there was, in an important department in an American university, there was doubt if it was true physics what Clauser was doing. I finish with these words. I think that nowadays this bias against Bohm's hidden variables no longer exists. Even because after Bohm's death, a little before, but during the 90s, there was a huge development of Bohm's ideas, and a kind of conference as this you are organizing is an evidence of the scientific interest in this approach. But in November 2022, when the Swedish Academy announced the Physics Nobel Prize for Clauser, Asper, and Zeiling, and they also released, which is usual, short historical retrospective about the prize. And in this retrospective, for the press conference, they cited Einstein, the EPR, they cited Bell, but no mention was made to Bohm. No mention was made that between EPR and Bell, there was a very important link that was Bohm's 1952 reinterpretation of quantum mechanics. Then I was very glad that Physics Today presented a more comprehensive description of the prize without leaving Bohm's names aside. Then I end my talk with this statement. Memory in science as well as in society is subject to struggle and reconstruction. Thank you very much.
Well, thank you, Olival, for that very fascinating talk. Sounds like really the debate was not what the answer is, but whether to even ask the question. So and that's really where he ran into trouble. Questions for Olival?
Thank you for your talk, Olival. So, just to add in your last comment, in this historical presentation of the Nobel Prize, Klaus, everybody who makes these experiments, in the historical presentation of the Nobel Prize, they say, well, these experiments ruled out hidden variables. They say this in the historical resume of what are the achievements of Klaus and Elling and all these guys. They say that it's wrong. They say a wrong thing. So this is also very.
You are right. I would say that I saw in my life a number of physicists here and abroad to say exactly these things. That Bohm's hidden variables were discarded by Bell's experiments. And you need to emphasize that what were discarded was not Bohm's interpretation, because Bohm's interpretation is as non-local as quantum mechanics is. Okay, you are right. Good.
I just wanted to point out a quick correction to the number that you gave for the citations for Bohm's paper. It's not order of 4,000, it's order of 9,000. 9,000. I just checked it on Google Scholar.
This, let me comment, because I took these slides from my 2015 book, which means 10 years ago, the Quantum Descendants. It's a book I published 10 years ago. And I was preparing the slides in a hurry, and I just took this number. Then this number, 9,000 citations, it's really impressive. Really impressive. Yeah, very, very. Thank you.
Maybe a personal comment which supports what you said about Bell. In 1987, I met Bell in one of the conferences and asked him if I can do a postdoc with him. So he said that if I'm doing high energy physics, it's okay. But if I want to work on foundations, then he cannot do this because he gets money for working on high energy physics.
Professor Lev, this is similar to what Bell said to Alain Aspect in 1975, when Alain Aspect went to meet Bell to present his proposal of experiments. And the first question from Bell to Aspect, it was not about the content of the experiment. It was, do you have a permanent job? And it happened that Aspect had a permanent job, because in the French system, he had already the doctorat, the troisième cycle, and he had a permanent job at the École Normale Supérieure Technique de Cachan. So this kind of thing that Aspect and Bell called the stigma against hidden variables was so widespread that we can collect this different number of testimonies.
Okay. Brilliant talk. Thank you. I learned so much from that. Could I just ask you one thing? Was that you talked about Bohm's interest in experiments, which I totally agree with. In Birkbeck College at that time was a physicist, was an experimentalist called David Butt, B-U-T-T. He's always forgotten in this. He was actually talking to Bohm and Basil. It's Basil I got this from. right, saying about the EPR experiments. And at that point, this is when these detectors were literally came on the market to be able to do it. And he was the one who was proposing. Now, I'm not going to be mean here, but Aspect visited the lab there. And he said, this is very interesting. I'm going to go away to Paris and do it. But which is nothing wrong with that. That's absolutely fine. I think that's absolutely fine. What I get slightly peeved with is that David Butt's name gets left out, because he was actually the guy who was actually starting to. He actually ran the EPR experiment, but his lab was a bit small and he couldn't do it over a very wide baseline. And then and Alain said, "Yeah, do you know what? I'm going to go back to Paris. I've got a bigger lab. I could do it over a much longer baseline." But I was it's a bit annoying that David Butt's name gets left out of this conversation. And I would like to remind everybody that actually did exist.
Any more questions?
Yes, thank you very much. I thought maybe I'd just share a little bit about some of the history, because I got to know Bohm in 1980 and then interacted with him in 1984 until he died, more on the philosophical topics. But it was very clear that he was himself, like in 1984, very interested in the hidden variables. Actually, he thought hidden variables wasn't such a good name because, like, decision is not really hidden. The decision is what we actually observe. But anyway, just as an example of that, Bohm remembered that there had been a sociological study by Trevor Pinch, an article something like, "What does a proof do if it doesn't prove?" And this was a master's thesis, and Bohm actually sent me to University of Bath to photocopy the master's thesis. This was, no internet at the time, and he read it, and there was also an article that Trevor Pinch had written, and his idea was it was kind of Bourdieu style analysis. The idea being that Bohm had, with the work in plasma and all that, he had collected capital, which he could then use to try to change the course of physics or change things. And Bohm himself he said, well, he didn't quite agree with that Bourdieu style of analysis, but just as an example that it was very important for him, the causal interpretation or the ontological interpretation at that period. And I remember it even once I asked him whether he would come to Finland and give a talk on the implicate order. And he just felt, well, there's not so much to say about that. I mean, he was like really focusing on that causal interpretation during that time, at least in discussions with me.
I had a question, if no one else has one, a little more technical. So at the beginning of your talk, you talked about the spin singlet state. Are you saying correctly, in speaking of EPR, that he was the first one who had the idea to sort of frame the EPR problem in that way, in terms of coupled spin states? Or?
No, I don't think that he was the first one. I tried to attenuate my statement saying that he was not anticipating the EPR in these terms. But you want to say that he was able to simplify the presentation of J. Duncan experiment, a thought experiment in this sense. But in the 1957 paper by with Haronov, they already used the singlet states to take the data from the experiments by Madame Vu. But this was 1957, not the textbook 1951.
Well, these have been some fantastic questions and comments after a fantastic talk. Let's thank Olival one more time. Now, tomorrow we have a very long program, so please try to get here no later than 9 o'clock, which is when we plan to get started. Hopefully this first session, though, has given you kind of a flavor for what this conference will be like in terms of the diversity of talks, and we have lots more to come. Thanks for coming.